Yep. Cheers. I just wanted to say hi. And we can shift it over to the stage channel if you want to do that. I'll send out a notification as well, just like an at everyone notification, so people know you're gonna start. And then we can get going. And let me know if you need anything. And
yeah,
we can doing a presentation and then a bit of a discussion afterwards.
Oh, yeah. And Icy Spin is wondering if he can participate. He was hoping to be able to participate as well.
We'll send that up to the office to get that cleared.
Okay, yeah. Does that go to the other campus, or does that stay in this administration building?
The satellite office. Besides that,
it's the satellite office orbiting the globe. Oh, that's great. All right.
What's up, MC2? Happy New Year.
Yeah, thanks. I see Gleam, you're in here. This is pretty late for you there. Is this like, are you between, because you're not working a lot this week because it's between Christmas and New Year's? Or is he not? Oh, he's in the text chat, but not in the talk chat. It seems. Okay. All right. Gleam said to NASA Shill, who welcomed me, says, stop distracting him. He's putting on the clown shoes. Now, so you know, Gleam knows that the Earth is a globe, but he argues for flat Earth basically just academically. It's kind of funny.
I think you'd get better at it after a while.
You know, with practice you get better at things, but not, maybe that's an old wives' tale. I don't know. Do flat earthers celebrate New Year's? I think they do because the year at least does. I think they do because the year at least does a it starts new. But there are some that insist on using a different calendar. They're like, I use the Enoch calendar, but the problem is the Enoch calendar is one less day. I think 1 or 2. So you can't use it for very many years because it will eventually start to drift.
But by the time your great-great-grandkids have come around, it might be lined up again for them.
Yeah, 364 years from now, it's all lined up again. So, no loss, huh? So Welch's 11 says Geo is the super Poe. Does anybody think Geo is a Poe? That's new. Galeem says it's 4 a.m. and I've done 4 3-hour debates on his channel. I'm pretty sure me and Toon have said all. Yeah, I mean, I was just greeting him. I was just. Robert Silverman says, how many rotations around the flat Earth of the sun is 1 year in flat Earth land? According to pretty much all the animations I've ever seen, a year on the globe is a year on flat Earth. Just the sun is magically with no reason floating over the flat Earth, and it's just doing circles. What makes it go in circles? Don't know. What makes it move in and out of the tropics? Don't know. What keeps it up? Don't know. But it does it. Trust me, bro. Nico says Geo is not a Poe. He is quite decent. Well, Geo's always been plenty nice to me, and I didn't think he was a Poe, but some other people were suggesting maybe he was. So, Gleam says they don't believe you, Toon. They think I am defo flat. Well, I mean, unless Gleam has changed his position, Gleam at one point had said that he given the choice would go globe. So, all right. What's wrong with what is this? All right, this formula here. Is this the same? Oh, it's melodic lyrics. Here we go. I don't know this formula offhand. All right. Melodic lyrics says my position is Gleam is as much of a flat earther as Bev. I disagree. Gleam can have an intelligent conversation. Bev is pure troll. Number 1. Number 2, Gleam has said he would bet on globe, and And Bev will only play semantics games. So, oh, Mr. E-Man said he's been following for a year and hasn't been recognized. Recognition to you, Mr. E-Man. Tad is mad for $2. Says 1 year on flat Earth equals 2 years on concave Earth. Man, oh, that's nice.
McToon, have you talked to Gleam on the voice chat or in the text chat? Because in the text chat, I think he's equally dishonest as Bev. Because in the text chat, it's easier to pull out those tactics. You can just ignore some of the people's messages and misrepresent what they say. It is much easier. But in the voice chat, if you have live conversation, it would look much more stupid. So I think he's much weaker in the voice chat and much more honest because of that. But in the text chat, he's pretty confident to act like a troll.
Well, I guess that makes a good point. I've had several conversations with him by voice, so that's most of my conversations with him. I haven't done a lot of text chatting with him.
I've done both. Actually, he did debate me a couple years ago, and he was an entirely decent person during the debate and actually conceded all my major points, as I recall. Unfortunately, I can't find the recording. So he's definitely different in text than in voice.
I can fully confirm. I also once got him into the voice chat because I made fun of him that he is afraid of going there, and I think that annoyed him, and he went there, and indeed, he really didn't push on any of those points that he argues in the text chat. He wasn't even trying.
So he's a little different, you're saying?
Yeah.
It may be that AI has taken over his keyboard, but not his VC.
Oh, that could be. That could be. Let's see. My mom bakes cake says 1 year TFE, 1 year of cope, 10 years of no flat evidence. I think it's at 11 years now. Eric DeBay's first video was November, I think, of 2014, November or December. Gleam says, "Thank you, Sir Toon. You know me better than anyone here. Either way, well, I know you pretty well. I like Gleam. He's good to talk to. Oh, I got it.
Your evidence is just what if, right?
No, but thanks for saying so, DMOC. I do appreciate your humor. All right, just for those in the YouTube chat, I got this for this Owala. Oh, I got it.
Your evidence is just what if, right?
No, but thanks for saying so, DMOC. I do appreciate your humor. All right, just for those in the YouTube chat.
Your evidence is just what if, right?
No, but thanks for saying so, DMOC. I do appreciate your humor. All right, just for those in the YouTube chat.
Your evidence is just what if, right?
No, but thanks for saying so, DMOC. I do appreciate your humor. All right, just for those in the YouTube.
Your evidence is just what if, right?
No, but thanks for saying so, DMOC. I do appreciate your humor. All right, just. Oh, I got it.
Your evidence is just what if, right?
No, but thanks for saying so, DMOC. I do appreciate your humor. All right, just for those in the YouTube chat, I got this for this Owala beverage container, and it's a Tron beverage container. All right, Nico posted a picture of Mr. Bean. Look at that. Geo about appealing his ban. Whatever.
I predict he has 2 weeks top if he gets unbanned before he gets rebanned.
All requests will get sent up to the office.
Into the circular file, as they right.
The Mars base, yeah.
Yep.
Where you keep your
Right.
proof and how you study a ball in a circular file.
Yes, DMOC. Thank you. Thank you very much, DMOC. You're the best. No dirt between. All right. Invited to speak. There we go. All right. All right. So people know I'll be doing a little presentation and then asking for input from the flat earthers here. All right. Looks like we're here. All right. How you doing, Gio? Let's see. How do we see? Oh, if I click, no. Invite to channel. I don't know how to see who's in the audience. It can't seem to hear you, says Gio. Really? I was talking before, but yeah, now it maybe can't. Yeah, it says it looks like. I hear you, Noah. Oh, all right. NASA Shield says I hear you. Okay, maybe it's just Gio. I don't know. All right, got this crazy idea. What if flat earthers are wrong about their flat earth theories? Says Hermit. Interesting. All right. All right. Jesse says, Gio, I don't even see your green circle lighting. The orphan system says, hey, Toon. All right, so it sounds like we're ready. And now Gio's not even in. Gio's gone. It's just Noah. The reins have been handed over to Noah. That's dangerous.
Yeah, can you hear me now?
Back. Okay. Yes.
Okay. Yeah, I don't know why you couldn't hear me before I was talking, but I just left and came back. Yeah, if anyone wants to join on the stage, you can just there's like a little button that says request to speak. But it sounds like if you're going to start with a bit of a presentation, then maybe there won't be people needed up on the stage right away. And then I can also, are you familiar with running the stage channels with the moderation permissions?
Me?
Yeah.
I am not. No, I'm
okay.
not.
Okay. Well, it's not. It's just if you wanted to, I can give you like a guest moderator role. That way, like when people request to speak, you can click to bring them up, or then remove someone off the stage if you want to too. If you're familiar with how to do it, I can do that. If not, then we can just kind of do it in the background for you. You know, like the mods can help. Either way.
Yeah. You could. I mean, I don't know how to do it, and picking that up on the fly might be a little bit of an ask, but I don't know. Maybe you could have somebody. Maybe Icy Spin could handle it. just not queue up. Anybody would queue up. All right. Oh, the Crunk Debunk is here. A TDDS, you need to change your name to the Crunk Debunk Show with a K. Okay. All right. Well, I'll tell you what. I'll start with what I have, and then we'll see who has anything to come with it. So, for over 150 years, the modern flat Earth position has been distinct from the ancient flat Earth position, where the sun is above the circle of the Earth. The ancient position was that the sun went below the Earth, or through a tunnel or a river or a portal of some sort. So in that time, then, of course, since Samuel Rowbottom popularized it, and I use that term loosely, in the mid 1800s, he published a book in 3 different revisions of the book, and I have some screenshots from like a kind of updated version of the third revision of it from, I think, 1881. And it was specifically experiment number 15 that he said he did. And so he said in his book, from the first floor of the Grand Hotel opposite the New or Western Pier at Brighton in Sussex, and I had a flat earther from Brighton in Sussex on earlier today. He said a well-constructed instrument called a clinometer was leveled and directed toward the sea. The water seemed to ascend as an inclined plane until it intercepted the line of sight at position H1, as shown in figure or Western Pier at Brighton in Sussex. And I had a flat earther from Brighton in Sussex on earlier today. He said a well-constructed instrument called a clinometer was leveled and directed toward the sea. The water seemed to ascend as an inclined plane until it intercepted the line of sight at position H1, as shown in figure 44. And I'll drop that into the chat for everybody to see right there. There you go. That's the first part of it. And then the second part of it here, he said, the next page, it says, on taking the instrument to a higher position, again leveling and looking over the sea, the surface seemed to ascend a second time until it met the eye at H2. The instrument was then taken to the highest room, which is about the 11th story, 10th or 11th story. And, are you looking for the puppy? All right, sorry, my wife's looking for the puppy. H2, let's see, to the top room, the Brighton Hotel, the Grand Hotel in Brighton is about 10 stories or 11 stories, depending. Maybe there's up the penthouse it might have been in, and it's not much higher than the ocean. So it's maybe the equivalent, maybe it's 120, maybe 130 feet in elevation. The instrument was then taken to the highest room and again directed to the sea when the uprising surface was again seen to meet the eye line as at the position H3, as already shown. These results are precisely those which an optical or perspective law produces in connection with the right line or a plane surface. Upon a globular surface, the appearance would necessarily be as seen in figure 45. Now, I do understand that the geometry he's claiming there, and I agree with his claim of geometry of what it should see for the flat Earth. And so this is what we're going to be asking is talking about that particular thing. But then he does produce, he talks a little bit about what he thinks the globe prediction would be. It says, from the position A, the horizon would be seen at H1 and at a considerable angle downward. How much of an angle he does not produce any prediction for. From B, the horizon would be at H2, and from C at H3, and the downward angle or dip would increase as the altitude of the observer increased. But as nothing of the kind is anywhere to be seen and the direction contrary to all times visible, we are compelled by the force of practical evidence to deny the existence of rotundity and to declare that, quote, to all intents and purposes, unquote, absolutely and logically beyond doubt, the Earth is a vast irregular plane. So now, the thing I'm curious about is if people do in fact agree with the assertion that he said, as already shown, these results are precisely those which an optical or perspective law produces in connection with a right line or a plane surface. That's one thing. The other then is, of course, the actual instrument that he calls the clinometer. He does, in a different portion of the book, describe it as an 18-inch iron tube with a string over the front and back, and he has a level on the top of it. So the string, the margin of error of this clinometer is unspecified. Unspecified and unknown margin of error on the clinometer. Anyway, so the question I have then to the flat earthers present is, what is, do you agree with Rowbottom's geometry, or do you disagree? And is there something wrong with it that must be corrected? And if so, what is that correction, so that I may refrain from strawmanning any flat Earth position? So that's the presentation, and so now I'm asking simply for assistance in either yes or no on agreement, and if no, what is the correct geometry or law of perspective for flat Earth? Let's see. We got Noah. We got Taking Back Eden. We got Finky is typing. Anybody got I mean, I guess if nobody has any, right? I'm on a Flat Earth Discord server. We've got 40 some people here. Certainly not all of them are of the flat variety, but I'd say that a good chunk of them are. And so if I think the geometry is fine. So if you don't have any issues with the geometry, I'll just take it to say that you're okay with it too. Anything? I see Jesse has popped in.
Indeed.
Yeah. Jess, any thoughts from you, Jesse, on that?
Well, I would think that the predicted, or that the geometry's perspective would have to match about 8 inches per mile squared, since that's what we observe in reality.
I'm at Jesse, get on task here. I'm asking, what is the geometry for flat Earth? Do you think that robot is geometry correct for flat Earth? So, oh, sorry, somebody else was. Who's that? Man, it got. I was in here the other day, and people were pretty noisy and over talking a lot, and now, man, kind of quiet.
From what I'm seeing in the diagram, it's basically just basic flare perspective, where they kind of rise the ground up physically as if it was a perspective drawing, even though it's actually an orthographic drawing. So I wouldn't say that's a correct prediction.
Yeah, the drawing I think is a little goofy. It looks like an orthographic drawing, but they're trying to make it into a perspective looking drawing. But apart from the drawing, I think the geometry isn't 100% perfect, right? Because at 120 feet elevation, 120, let's call it 150. That's kind of, probably a fair amount. Now Brighton is looking south, and so from there south to the edge of flat Earth is many thousands of miles. So the right triangle that's formed from that is creates an angle that's exceedingly small at 130 feet elevation, 150 feet elevation.
Is your main question like whether the horizon should rise to eye level if Earth is flat?
That is the claim from Rowbottom, and I'm asking if I'm actually more asking what is the method for predicting the amount, because it's not exactly zero. Right, it creates a triangle, and that triangle does have an angle, right, from the observer to the edge of whatever you can see, and so it's a non-zero angle. But if you're at 150 feet and the distance is many thousands of miles, the angle is going to be somewhere less than 1,000th of a degree.
Yeah, and I guess you'd have to know where the edge is. You'd have to know where the edge is too, because there's some flat earthers believe in an infinite plane, so that would go on forever. So the angle would
the angle would be zero. It would be zero in that case. Yeah,
correct,
it would approach zero as it goes to infinity. So if it's less than an infinite plane, then it is a non-zero number, though it's very small. So
what was the observer's height and the distance?
Well, the observer's height is 150 feet. Being it a little generous, it's an 11-story or 10-story hotel, and it's on the bank of the ocean there. So
at least 2,000 miles to the edge.
Yeah, it's pretty generous to say. It's a very small number, right? It's certainly more than 2,000 miles.
Right. So at 2,000 miles, it'd be 0.0008 degrees.
Okay, 0.0008. So 8 10,000ths of a degree. Do any flat earthers have any disagreement with that? All right, hearing nothing, I'll accept that everybody, the 35 some people that are here are all in agreement. Okay.
And if any flat Earther isn't reading the text but does want to speak to Toon, just get in the text and tag me, and I'll put in a request to get you invited to the stage.
Yep. Yeah. I don't. I seriously. I was in here. I think it was yesterday, and man, the people were walking all over themselves to talk to me and try to say something, right? Try to, I don't know. Was SEM Montreal was there? Noah, I think, were you there? Jeremy was there. Just couldn't get enough. All right. Well, I'll go with the next step then is in the late 1800s, mid to late 1800s, the highest that people could regularly get would be a high hill that can see the ocean. There were balloons that people could ride in, but it was a little more of a challenge. So I can see that it's a bit of a challenge for people to do in the 1800s, and how it could be a compelling argument. But now we can get in airplanes, and in an airplane we can get significantly higher. So we can get, instead of 150 feet, people regularly are in airplanes that's 35,000 feet high, significantly higher. And the prediction for the globe is also dramatically more. So for example, the prediction for a globe at 150 feet is 0.0 something, right? So small enough that the clinometer that he had with the string over the end, an 18-inch iron tube with a string over the front and back, the margin of error of that is pretty sloppy. It's probably, being generous, a tenth of a degree. And my guess is that the globe prediction is less than a tenth of a degree. And Rowbottom did not. I don't know why. Maybe he couldn't do the math, or maybe he didn't want to tell people the math. He did not choose to produce the prediction for flat Earth in there. But I can, or sorry, for the globe. He didn't produce a prediction for the globe. So Northern Rebellion says horizon rises with altitude. Okay, so that's all right. So are you saying that it should be, it should follow the laws of geometry, Northern Rebellion, or is there something else to it? Right? Is there something? Do you disagree with Rowbottom? Rowbottom said it follows the laws of perspective. And let's see his exact words. So we don't want to. Right? He said, right? Maybe it's the first one. Okay, no. The first part is what he saw. The second part is the prediction. So these results are precisely those which an optical or perspective law produces. So the question then is, does this follow optical and perspective laws? And if it does not, what does it follow? I don't know why. All right, Northern Rebellion, thank you very much. I see that. That's exactly, I agree completely with that. So Northern Rebellion, are you saying, by this, I hope people can see this at home, that if, by posting this, Northern Rebellion, are you saying that if you were to measure and find that it matches the right side, that would be evidence for flat Earth? And if you were to measure and find that it matches the left side, that would be evidence for globe? Is this, I see this one posted a lot. Is this something that people other than just Northern Rebellion agree with? He said something. Northern Rebellion thinks there's no celestial South Pole. Well, that's silly. I saw it myself with my own eyes. All right. Well, I will take Northern Rebellion. I completely agree with you. I 100% agree that if the horizon does what's on the left side of that, then the Earth is a globe, and if the horizon it does has the right side of that the Earth is flat. So, thank you. I'm gonna, you know what? I love this one so much, Northern Rebellion. I'm gonna grab a screenshot of it. Where did it go? Did you delete it, Northern Rebellion? Did you delete it? Oh, there it is. Oh, good. That would have been embarrassing if you deleted that. Okay. There we go. There we go. Right there. Okay. So, so the next thing then is we can actually do the geometry for both flat Earth and globe. Now, I wrote a program in Python to compute the dip for flat Earth at different elevations. Now, the problem with flat Earth versus the globe is it matters what direction you're looking, because the direction you're looking and the location you are changes your distance to the edge, right? So if it's an infinite plane, it must be 0. And if it's a non-infinite plane, then the dip must be a little bit, but it changes. And when you're closer to wherever the edge is, that dip will actually get larger. So let me give you the flat Earth prediction. So here is the flat Earth prediction for different latitudes, at least applying the laws of optics and perspective. This does not include refraction, which flat earthers generally are loath to include. And what I've done here is I've given a range. The range of one is looking of so on the equator, for example, at 35,000 feet, flat Earth predicts, which does to do Northern Rebellion. Oh yeah, Northern Rebellion. I can't unmute you. I don't know if you, in this instance application here.
Are you intending to
I'll
speak?
take a long
Can y'all hear me?
Yes. Yep. Yeah, Taylor.
Okay. I have a question. Whenever you say what the flat Earth prediction is, are you taking into account like the requirements by like the Journal of Surveying and Engineering to get the temperature gradient in order to calculate the refractive index and which way the light's bending?
No, I'm asking for the flat Earth prediction, and if the flat Earth prediction includes it. Generally, flat Earthers don't include any of that stuff. So, if you want to, then that'd be fantastic.
Are you taking into account like the requirements by like the Journal of Surveying and Engineering to get the temperature gradient in order to calculate the refractive index and which way the light's bending?
No, I'm asking for the flat Earth prediction, and if the flat Earth prediction includes it. Generally, flat Earthers don't include any of that stuff. So, if you want to, then that'd be fantastic. But if you don't,
Oh, that would be awesome.
want to, so well, yeah. So
Because
then that's what I'm asking you. Then I'm asking the flat Earthers to critique the flat Earther Robotham's geometry here.
yeah, what you need to do is you need to just use like basic refractive calculations. And Jesse's done that before and helped me with some of my measurements. You have to incorporate the temperature gradient because I'm sure you've seen like the Skunk Bay time lapse where things are moving up and down throughout the day. Especially near water and areas of like, with water and high wind, that's gonna fluctuate even more. But generally, in all the peer reviewed papers I've read on terrestrial refraction, things will consistently drop throughout the day because that temperature gradient is changed in density because hotter temperatures, lower density. And there's multiple peer reviewed papers which have stated that light can actually cover upward along the horizon, along the surface, especially during the daytime with the sun affects heating the earth, and convection, causing that rapid heating of the surface of the earth and that drastic temperature gradient. So essentially the light curves up. And this is why, they've done hospitals, they've tracked hospitals, mountain peak to mountain peak in the Swiss Alps, and somewhere I think in Arizona along what is it called, a valley, where basically they're looking at a mountain peak. And all three of them, they see the mountain tops move throughout the day. The most recent paper I read, the Swiss Alps paper, was mountain peak to mountain peak, and over 2 kilometers, it dropped, I think, 31 centimeters, around 31 centimeters during the daytime.
Okay.
That was the vertical displacement. So what you need to do is you need to just incorporate the temperature gradient whenever you do any readings. And that's not me saying that, that's peer-reviewed paper saying that, so you can see which way the light's bending.
Okay, so I've intentionally used elevations that's significantly higher than that because it's not as much about the temperature gradient. It's the pressure gradient that has the primary effect at elevations like 35,000 feet.
Well, the mountaintops still experience the same temperature gradient as any other ground would. It basically absorbs the sun's, the sun rays and heats up throughout the day. And this is why the last paper I found was very significant, which I can send to you. It was done from mountain peak to mountain peak in the Swiss Alps, and it was looking at the vertical displacement. So that effect is still present.
Yeah. So yeah, I'm not denying that. But I'm saying that at 35,000 feet versus a mountain of 10,000 feet, for example, is a pretty significant mountain. 15 is even more. That the gradient is primarily driven by pressure, not temperature.
Yeah, you can cite that. But from the papers I've read that have actually studied the vertical displacement of the mountains throughout the day, well, the pressure gradient is pretty stable. I mean, apparently the temperature, higher temperatures can affect pressure, but either way, pressure is pretty stable. So that's why temperature gradient is the predominant factor in terrestrial refraction. And, I would assume that's what's causing the mountain peaks to have vertical displacement in daytime.
Yep. So I put in a citation there, mctoon.net/refraction, and then I will put in the pressure gradient right there, citation. That's US Standard Air 76. Cited both of them. So
yeah. So back in the day, whenever you look at the papers, if you start reading the papers on how they calculated standard refraction, what they did was they actually, took the pressure gradient, right? But for the temperature gradient, they use weather balloons. So they do 1 point of temperature every 100 meters or so. So that temperature gradient is not reflective of the bottom layers of the atmosphere. There is multiple papers that are very recent by credible journals like surveying and engineering, geophysics, atmospheric modeling, whatever. Multiple different like journals that have multiple papers. So basically, they're saying that the standard refraction is not representative of the bottom layer of the atmosphere, because whenever they did that temperature gradient, they were doing it in such high intervals, and the upper atmosphere temperature gradient does not represent the steep temperatures we see as we're standing on the ground. That's I mean,
I agree, and that's why the elevations of 35,000 feet are used, because it avoids the specific ones that you were talking about, the low portion of the atmosphere. It avoids it.
But what I'm saying is, I mean, I've heard that feedback as well. So then what's causing vertical displacement from one mountain peak that's like 7,000 feet off the ground, the Swiss Alps, to another mountain peak 2 kilometers away to have a vertical displacement of 31 centimeters? What's causing that during the daytime?
I don't know what you mean by 31 centimeters. These displacements
Okay, I'm gonna give you this
angles.
paper.
It's measured in angles.
Okay, that vertical displacement in this recent paper is from the angle that they're measuring it. They basically were tracking the mountain peak, the optical apparent mountain peak, and throughout the day, even at that elevation,
what was the angular displacement?
I don't know. It equated to, I think it was like 10 megagons or MGON. That was what was on the chart, and that translated to 31 centimeters. And hold on, it's hard to talk and get this paper for you. I'm trying to send it to you, but either way, from mountain peak to mountain peak at high elevations, you still see this vertical displacement. And that's because you have temperature gradients experienced on mountaintops as well. Even if the line of sight isn't, it seems like where the observer's at and what you're viewing, the fact that the sun is causing heating effects there, you're still going to see that apparent shift.
Okay. I won't interrupt you while you get that to post.
So yep, I'm doing it right now.
Post it.
Mm-hmm. Mm-hmm.
All right. I have my notes ready, so I can put it in when you put it there. So, the issue is that at 2 kilometers, 31 centimeters is a rather small angular measurement. So it's smaller than the margin of error of the measurement that we're looking at from an airplane.
Ironically, that's how much Earth curvature, like within a centimeter or so, is how much is over 2 kilometers. I found that to be so ironic. I'm dropping the paper right now. But yeah, they repeated it multiple times. Yeah, 10 megagons, apparent height change of 30 centimeters. I'm sorry. And I think over 2 kilometers, it is 31 centimeters in total. And hold on, copy, paste. Okay, do I drop it in the chat right here? Yeah, live stream stage chat.
32 arc seconds.
There you go. I just dropped it in the live stream chat or whatever.
Is it audience text or live stream one text? That's what I'm looking at. Oh, here. Hold on. Somebody.
I actually DM'd it to you. I DM'd it to you as well.
Oh, okay. Thank you. All right.
Yeah, I don't expect you to like go over it right now. Like,
yeah,
I don't like when people do that to me either. I can't like read a whole paper in 5 seconds. So yeah, just read it whenever you have some free time. It's all good.
Okay. So to be clear, and I'd love this if you did agree with it, taking into account the effects of refraction are important. Is that your position?
Yes, I think that it is. Yes.
Okay, because it's common for flat earthers to intentionally ignore the effects of refraction.
I get that, but look, the thing is, and in multiple other papers, which I can drop as well, is they are saying this standard refraction should not be used in surveying because close to the ground visual optics are significantly affected by the temperature gradients, which is the predominant effect factor in terrestrial refraction. I'm sure in your studies you've come across that. I think
absolutely.
You've reposted that.
Yeah, I cited I mctoon.net/refraction as a whole collection of papers on refraction, and at low elevation, later in the day, especially and over water, even at the most, the effects of refraction are maximized, and you can get dramatic coefficients of refraction at low elevation. So the better conditions would be in the morning on an overcast day when it's cool. And so, if that's done, then you get minimal refraction, and ideally the water temperature and the air temperature would be the same. There's still going to be a somewhat of a gradient, but that definitely helps. Okay, so
do you agree that standard refraction shouldn't be used though? Like I can send you some sources on that too.
Yeah.
Assuming,
So standard refraction, and there is no standard refraction. Some industries use 7/6, some use 4/3. The U.S. Meteorological Society, for example, uses 4/3 or 0.33. If you're going to use, and this is not over water. This is a point to point above ground only. The U.S. Meteorological Society uses that. Maybe it's called the American Meteorological Society. And so you use 0.33 if you're going to use the Bislin calculator in order to do that. But if you're over water and you don't know the conditions, the bare minimum is 0.5 to just as a rough number to use over water at low elevation. and that's being quite conservative actually. So
is that always assuming light curving down?
Yeah, light generally does curve down, and there, like you said, there are instances where it's possible, but it's an unstable condition, because in order for light to curve down, you have to have denser air higher and less dense air lower, and that's unstable because the dense air wants to go down. That's convection. So that's where you get these really wavy conditions where it's moving around like that, and the air is exchanging places. That's why you get kind of, it almost looks like something's on fire if you look across a field or something. Like, you don't see the fire, you just see the wavy lines above the field.
Yeah, but there's been papers who measure the temperature gradient along the ground. And like, if it's warmer, it's going to be lower in that density. And, it significantly affects density because pressure's like the pressure gradient. Whenever I measured it, I couldn't even find one in the line of sight I was viewing. That's how minute it is. So whenever you get that higher temperature, you're going to get that. And I have a paper I'm about to drop you that was done for some temperature measurements in it cited Henny's 2006, where they were doing like temperature gradients along the ground. And they said they actually, calculated a concave curvature of light along the ground in practical temperature measurements. So it seems like it could be more common than you might think to have upward curving light along the surface.
Yeah. Well,
you don't even need a gradient that strong.
Yeah. Well, you need some sort of gradient. If there is no gradient, if the index of refraction is consistent, then the light won't bend.
No, the temperature gradient doesn't even need to be that strong to get it to, affect the density. Yeah, the density can easily be overthrown through temperature gradients that are not even that
temperature. High. Yeah, the temperature gradient is much at low elevation, especially since the temperature varies so much. The temperature is the predominant factor in the coefficient of refraction. And I'm throwing around terms, and Tayler, maybe you know this. I don't know if others do. Index of refraction is what's used in Snell's law. That's the relationship of the speed of light between two different mediums. And you don't need to go between
atmospheres / volume 115 issue D21.
This instance of 1 degree Celsius over 10 meters, you get a coefficient of refraction K of 1.0. And that's pretty strong refraction.
Yeah, so right here, this is the Journal of Geophysical Research, atmospheres / volume 115 issue D21.
Did you
and
post
it says,
this?
I'm posting it right now. Oops, I just totally lost it, what I was reading. Oh my gosh. Oh, I found it. Okay. I just wanted to cite the journal, so I had to click on the link. Okay, here we go. I was just going to read this. Over the day, the sun radiation is being absorbed by the Earth's surface, and the warm terrain in turn heats up the lower atmosphere layers, resulting in negative vertical temperature gradients and turbulent motions of air called convection. For example, a gradient of negative 0.5 kelvins per meter derived from practical temperature measurements by Henny's 2006 translates to a local refraction coefficient of negative 2.9 compared to the Gaussian value, which you were talking about earlier, of positive 0.13. This describes not only a stronger, but also a concave curvature of the path of light, i.e. opposites to Earth curvature. And I'll give you that link.
Yeah, that's good. So Gaussian being, so Gauss, a German guy, a scientist that spent a lot of time measuring the effects of refraction from mountain hilltop to hilltop for many days. And so he when he says Gaussian value, it's the 0.13. That's the value that he measured. That's the coefficient of refraction of 0.13. The standard, what's often called standard refraction, is 0.17, and then, like I said, the American Meteorological Society uses 0.33. So I don't see that you posted it though. You must be posting it in a different place.
Okay, this one is in the live stream stage text. I think I DM'd it to you as well.
Oh, okay. Well,
yeah, I DM'd that one too. I DM'd it with them and posted
okay, I got it. That's the best. Awesome. Thank you. All right. Well, I'll have a look at those, because I totally agree with that. That's the kind of stuff that you need to take into account. And again, those are at low elevation. What is it at 35,000 feet?
Yeah, that's still
The
the ground
paper she
though.
just
Like,
cited was like under 3. I think it was 3 meters and below. They were really
Yeah,
close to the
yeah.
ground.
but there's other papers that said that up to 100 meters at least near the ground, right, is going to have these temperature gradients that are much different than the upper atmosphere, which is what they're actually using to get this standard diffraction. Like I said, they go every like 1 point every 100 meters. Like, you cannot calculate that and assume that's going to be on the ground. And by the way, if we want to be technical, you can't assume any refraction. If you want to be accurate, you have to actually measure the temperature gradient. That's what the Journal of Surveying and Engineering suggests you to do. So I don't want to make any assumptions. I want to tell everyone when they're doing their measurements to actually take that gradient. Like, I have an RTK thermometer. It's a research grade thermometer, very reliable. You can get temperature gradients, even like in where you're standing. And, I attach some pressure and temperature sensors to my drone to try to get some line of sight stuff to account for the pressure, temperature, and humidity gradient along my line of sight. That was a little bit more technical, but yeah, I mean, at the very best, just like measure your gradient, like just
The
like
problem with the
simple.
challenge with using a drone is that it mixes the air.
Yeah, but that's why you have to hang out. Like, this was Jesse's idea. Thank you, Jesse, for giving me the idea of using a very long fishing line and hanging my pressure, temperature, and humidity sensors from it, like significantly far away from the drone.
Yeah,
And I have a
help,
DJI
yeah.
Mini, so it's not it's very lightweight, so it wasn't strong winds it was putting off. And I flipped them
Yeah.
and everything to make sure it was like all good.
So yeah, Finky is typing, says Tayler agreed that we should throw out all black swans and laser tests from flat earthers. Right. I don't know if all is maybe a bit strong to
Well, if we do
throw
that,
out
then y'all
all of
then
those kinds of measurements.
okay, well then anybody who didn't account for the refractive index would need to throw out all your theodolite measurements too. I'm just saying, if you want to do that.
I'm happy to not use any of those because that's not necessary to determine the shape of the Earth.
Wait,
Right?
you're not. Wait, what'd you say?
I don't need to use theodolite measurements to determine the shape of the Earth. There's many other ways to figure that out. If we can't be precise enough with those.
Well, what's your
Right.
favorite? I'm just curious.
Well, I like the dip of the horizon, like I brought up here, because it's so commonly cited by flat earthers, and it goes back directly to Rowbottom Experiment 15, and he was so sloppy in it, and but I think the azimuth to the sun is a fantastic one.
The
Right,
azimuth to the sun.
Yeah, the azimuth angle. That's the horizontal angle. The horizontal angle isn't affected by refraction like that.
But are you assuming like a size and a distance for the sun?
Nope. There's no assumed size or distance to the sun in that.
Okay. So what do you assume? Parallel light rays?
Nope.
Okay. Yeah, I mean, you can go ahead.
Just that the sun is in a position, and that's it. You don't need to know the size of a light bulb to know where it is.
The sun being in a position means the Earth is a globe. I don't get it.
Well, no, you can apply the right. You can hypothesize that the Earth is a globe. You can hypothesize that the Earth is flat, and then you can apply the geometry of either of those, and determine the horizontal angle that the sun must be at for any particular time, based on the model. Now you can vary the model. You can have multiple different types of models that you can try. The most common model, of course, is the Gleason map. It's been the only one that flat earthers have really proposed regularly in the last 150 years. And so we can take that, and you don't even need distances on that. You can just say, well, here's where the sun is on this day according to the Gleason map. Here's where I am at the moment, and what is the azimuth to the sun according to this map. And then you can do the same thing applying the geometry of the globe and the solar system, and say, well, here's the angle to the sun, the horizontal angle to the sun on the surface of the globe here at this day, at this moment. And so then we have two different hypotheses, and we can see which one matches. Now, that's not really our
Is this
topic
the
for today. I
sticks
don't
in
want
the
to get too
ground?
far.
I'm just curious.
No.
Last question.
No,
Sticks
it's
in the
not
ground?
sticks in the ground. Nope.
Okay. Okay, whatever. Send me a link.
No.
Yeah, I'll get it.
So an azimuth is a horizontal angle, and a zenith is a vertical angle. So sticks in the ground would be measuring the zenith angle. So I'm talking about the azimuth angle.
Okay, yeah. Send me like what the hypothesis, like what the prediction would be for each model, and then like what you and how you record it. I'd love to try it. Like I'm totally like I do research and I love doing experiments. So I really absolutely love this type of stuff. Like this whole conversation is very interesting to me. So yeah, like if you have like a hypothesis, like what you predict for each model and how I could test it with what like equipment, like let me know. I'd love to do it.
Sure. All right. All right. Taking Back Eden is talking smack here, but he's not in chat to bring to
Didn't like that.
Tayler. I know. I got to give him a little bit of crap to to bring to address the topic.
He's
All right. Hey,
sweet. Don't talk about Eden like that.
Tayler, I know. I got to give him a little bit of crap to get him up here. But thanks, Tayler. It's always good to talk to you. All right, we got some more. Some more sitting in here. I don't know, but none of them sitting in here are named Taking Back Eden, who is.
Hey, can I ask you a different question?
Okay.
Have you talked to Dave about the dual pole? What are your debunks to that?
Dave who?
New Perspective. Sorry. New Perspective. He's been, sharing a lot of things on the dual pole model. Do you have any like debunks or anything?
So, on Facebook, people like to post. Globers like to post a picture of the edge of flat Earth with the boat tipping over it, and of course, flat earthers are like, "That's not our model. We don't believe that." So it's funny because the dual pole model is that exact thing there. Now you don't have Antarctica around the outside anymore. Now you've got ships falling over the edge. And I don't know, is the turtle eating them on the way down? So there's one.
You can still have an ice wall. Like I've talked to them, and I think that they believe you still can have an ice wall with Antarctica being like a continent at another continent at the bottom near like the south pole of the magnetic pole.
But the equator goes right to the edge. It's hot.
Yeah. Yes. Yeah. The hot equator goes to the
But
edge.
it curves.
The equator doesn't curve. On that model, on the dual pole model, the equator is straight. So the
It does
equator.
at the edges.
There's two
Not of the
equators.
ones I've seen.
There's an equator around the outside and then one across the middle.
Oh, well, all right. So the other problem with that, of course, Hawaii is farther from the equator than Washington. Redmond, Washington, for example, in that map, which doesn't make any sense because, of course, Hawaii is actually much closer to the equator. Yeah, there you go, Jesse. Thank you. You've got now south of it's quite incredible because you've got these distances and light patterns that are even more ridiculous than the previous Gleason map version, where you've got weird patterns like how does the sunlight make this pattern? Now you've got even weirder patterns. It doesn't solve the magnetic pole. Now you've complicated the magnetic field of the Earth even more.
Well, a magnetic field has a north and a south pole, like any like magnet, and an electric field does too. But I'm just saying, I don't know. I can send you some magnetic field pictures.
Well, yeah. What would the magnetic field look like on this? Because the south magnetic pole does exist in reality. And a lot of flat earthers, the kind of Dave Weiss version of flat earthers, think that the Gleason map just has a North Pole magnet in the center and that there is no South Pole. But in reality, the South Pole
this one does have, yeah.
Yeah, in reality, the South Pole is between Australia and Antarctica in the ocean.
I just tagged him, so if he's awake, because I can't defend it. Like, I just started hearing about it. Anyway, sorry to interrupt. I just want to hear your thoughts on it. Thank you.
Yeah.
We got a fun challenge for McToon. Try to come up with a better flat Earth setup. Hypothetical, of course. We know you don't think the Earth's flat. A better flat Earth setup than the dual pole setup.
I think the Gleason map solves it better because you have, you can go with Dave Weiss's, there's a ring around the outside keeping the oceans in, right? And it doesn't, the sun doing weird loops and doing basically kind of an annual figure eight
So the Gleason has a obnoxiously large Antarctica. Dual pole has a more normal sized Antarctica. So at least for the size of Antarctica, the dual pole is better in that regard. Just purely the size. We could take it one by one. If you really think Gleason's better,
other things are distorted though. Then, right? That's right. The distance. Look on the dual pole. Look at the distance from Hawaii.
Look,
seriously, look at it. It's to the equator. It's
the
ridiculous.
challenge isn't to say that the dual pole is works or I'm claiming the dual pole. The challenge is do you think you could come up with a point by point better than the dual pole?
So I do have one that's better.
All right.
All right, we're gonna get off track. I want to get back on track, but because I want to make sure that if anybody has something to say on this topic, think about it now. Come back to it in a bit. But let me grab. Let's see. The better thing. So if you go away from the Gleason map, you basically wind up having to do teleportation, right? Or pack moving. If you use like the one from the goofy one with the wavy equator from Awake Souls and Limitless, you Pac-Man. If you do with the one from Nesbit or Darren Nesbit, it's a diamond shape, you got Pac-Maning. If you got Arwen's Mercator projection, it's a Pac-Man. So if you're going to do Pac-Maning, well, just lean into the Pac-Maning. And don't just have one Pac-Man, have a bunch of portals. So all right, I'm looking for it. I don't remember what I named it, but I have it in this folder here. Australia is the same size, and everything's the right size as is measured in reality. But now you just have magic portals to go across them, unless you're on the equator. Exactly. Yes.
So when you're driving along on the freeway and the swings kabump, kabump.
There's a couple others more recently that have gone on. It's a problem for the upward rising Earth because it would have to be the same everywhere and homogeneous. So it can't work. So now you have to go back to not back to. You got to go to the next one. The next one is the roller coaster Earth. That's where the Earth is on a giant roller coaster in space, and it's moving around in a circle. It's trapped in a circle, going around, causing 9.8 meters per second squared downward acceleration, but a little bit less because gravity still exists, and the surface of the Earth is inconsistent and inhomogeneous. And so now you can have variations based on the mass distribution inside the Earth on the roller coaster. So there you go. It's that map, and it's on a roller coaster in space. How about that?
Yep, all good.
All right.
There are a lot of hands raised to come and speak to you, MC2.
Oh, good. On topic? He wasn't of circuit. The dip of the horizon for flat Earth is 0.02 to 0.040, depending if you're looking.
Absorbs the heat from the sun, and that'll still be radiating.
Because you can see, and that's some of the best time to do it because the horizon is very crisp when you're looking at it.
But that's because it has a stable gradient. Because like the sun's been out all day and it's still heated. Like the conduction of the Earth will absorb the heat from the sun, and that'll still be radiating. Especially right after it sets, that's still occurring. But it's just a more consistent gradient.
A better time would be then at sunrise when the it's had all night to cool down. So flying to the east as the sun rises would be an ideal time to measure the dip of the horizon from an airplane.
That's what. Well, actually, whenever they did laser tests, they were testing like what times of day have the best refraction, or like actually the least refraction. And they said the nighttime at night, like midnight, like 3 a.m. The temperature gradient. I'll drop some pictures in the chat. It stabilizes out the temperature gradient at nighttime, but during the day, afternoon, all that you got a steep negative gradient where you're gonna have upward curving light along at least along the surface. Now, how high does that go up? It would just depend on the day conditions. You'd have to measure that.
Yep. Yeah, and Taking Back Eden is showing the PBS documentary that was not cool. They faked it.
He also has his hand up.
Who does? Taking Back Eden? Or I don't see him, but yeah, if somebody else does, go ahead.
Yes, he's in the audience. He has his hand raised, as do a number of people.
Oh, let him in.
Yeah.
I'm going to put a picture in the chat. This is from the University of Georgia. Talking about how things would disappear bottom up with concave curving light.
Taylor, I think you're putting it in somewhere else than what I'm expecting. I don't know if other people are.
A live stage chat.
Live stage chat.
I don't know where y'all.
We're all in there.
I DM all to you too.
There it is. Okay.
If you're on a phone, it's right next to the mute unmute button.
No, I'm on a computer. I wasn't I was looking at the live stream one text, which is where the chat is. The people. There's a Biola.
On the globe.
Conversation.
I have some thoughts. So for me, calculating this based on the edge of the Earth is problematic because on a flat Earth, you would see basically infinitely far away up to the edge if there was no atmosphere. And on the globe, which is the reality, you don't really see that. That's why we don't really verify the
Need to know what something is in order to see where it is, right? If I can look at a light bulb, but there's a light bulb right there, right? And I don't need to know what it is to be able to point where it is, to measure angles to it, to measure the distance to it. I don't need to know what it is, right?
As long as you can visually see it, you're saying you can make kinematic assumptions about it or whatever.
Geometric. I can apply geometry, the law of perspective, the law of optics. Yeah, all of those things.
But unless you tangibly verify the height of something, how do you know it's
I can apply geometry, the law of perspective, the law of optics. Yeah, all of those things.
But unless you tangibly can verify the height of something, how do you know it's actually where it is?
Geometry and optics. Yeah, and there's no kinematics. That you probably didn't mean to say kinematics, right? Kinematics is about the study of acceleration.
Any object that you can see in motion. Yeah, any object. Yep. But that's not the point. Point I was trying to make is you say you know what a star is, right? Probably from some type of spectroscopy. But when you actually peel back the layer of spectroscopy, they're making massive assumptions between you and the star you're looking at, and what's in between you and the star.
Yeah, completely irrelevant to the topic though, because this isn't about identifying the chemical makeup or physical makeup of something. It's about where it is. So you don't need to know what it's made of to know where it is. That's a red herring, is what you're going for. So I don't care about determining what
we don't
is
have to go there.
You're
not.
Right. That's not what I care about.
But to know an angle, like to derive an angle from a celestial body, right?
Yeah.
How are you, like, what are you referencing? You're just referencing the ground in terms of the terrestrial globe or terrestrial sphere, and then you're linking that based off a radius of 3959 that uses like a fictitious observer at the center of the Earth, and that extends to the celestial sphere, and then that gives you the angle.
No.
That gives you the
I'm
60
testing
nautical
flat
miles
Earth
per degree.
I'm testing flat Earth. So when I test flat Earth, because I'm in a flat Earth Discord server, I'm here to talk about flat Earth. So when I'm testing flat Earth, we know a few things. We know that there is a position on the surface of the Earth, which is directly below that star, and these have been mapped out for centuries, right? Yeah, where the zenith is 90. Right, so it's the GP of the star. There's the GP of every star, or at least the 50 some stars used for celestial navigation, especially the GPs of those stars are well known, and we have 250 some years of documentation of the positions of those stars that we can easily access, that people have used in life or death situations for the last 250 years. So we know there's a high level of accuracy for the GP of each of those stars. Now, if the Earth were flat, right, then we can just apply very simple, seriously, it's 8th grade geometry to figure out their height, their position. That's all you need, right? If the Earth were flat, that's all you'd need.
Okay, well, you said you know the GPs of the stars, right, by taking a zenith, but it's only using a few stars, actually, and it's in the band of 20 degrees to, like, 70 degrees somewhat. How come you can't use the whole band?
The whole band, you mean? Why can't you use
90 to 0 in terms of...
Well, Polaris is one of them. So Polaris is certainly near the North Celestial Pole. And the stars near the South Celestial Pole, I think Crux, the constellation is used in celestial navigation. Just going
Right,
off
right.
of
But
memory.
I'm saying if you are
Like-
actually celestial navigate, like if you're using, like you're a mariner, right, and you're using a sextant, you're taking an angle to a star, you're using a dip correction, whatever, blah blah blah. You can only use a certain range of stars that are listed in the nautical almanac. The ones that are listed are usually between 20 and 30 and 70, or 30 and 70, depending on which volume you use. My question to you
30
is,
and-
if it's just a linear relationship because it's a celestial sphere transposed into a terrestrial sphere, then why can't we use the ones that are below 20 or above 70?
I don't know what you're talking about. Polaris is at 90.
If you're
Polaris
at
is
the
one
North
of them.
Pole,
No, you can use Polaris when you're at 20 degrees north latitude. You can use it. So you said you can't use them within this band. They need to be between 20 and 70. No, you can use the star that is in 89.5 degrees north declination. And you can use the stars of Crux, which are at, I don't know, 80. I'm just
usually the brightest,
top of my
you know,
head.
like Sirius
80,
or Orion.
80 degrees, 80 degrees south declination. So I don't know where you're saying that you can't use them in a certain band. The range is nearly the entire range of
there's so
stars of
much-
declination.
Because there's so much quote unquote celestial refraction at those angles that you wouldn't be able to tell how far away you are from that GP. And in a sense, the 15 degrees per hour relationship that you establish when using those stars for celestial navigation, like creating circles of equal altitude, etc. The reason why you can't use those stars is because it's not a linear relationship at that point. It starts
All right,
to move.
So
in
hold
a
on. Let me
unpredictable pattern.
verify. Let me verify what you're talking about. You're not talking about using the stars at certain declinations. You're talking about using stars at only certain angular elevations.
Yeah. When you're celestial
Okay.
yeah,
okay.
I should have specified.
Okay.
My bad.
So the older nautical almanacs actually do include refraction adjustments for stars all the way down to 0. But the precision is lower. And as Tayler mentioned, when you get lower and you're using more of the low atmosphere, there's more inconsistency. So that's why you don't want to use them, is because you're looking for precision. So if you're okay with a little less precision, you can do it. Go ahead. Use a star that's at 1 degree angular elevation. That's okay. Right? We can do that. It like when a navigator is being taught what to do, here's the best way to do celestial navigation. Use a star that's between 20 degrees angular elevation and 70 degrees angular elevation. Why is that? Because that gives you the best results when you're doing celestial navigation. Because when you're doing celestial navigation, you want high precision. You want to be within 2, 3, 4, 5 nautical miles of your true location. But for you and me, that's fine. We can totally do that. We can say, let's use that star. Let's be at the equator and use Polaris and draw a circle of equal altitude at that. That's okay, because we don't, it's not life and death. We're not trying to find the actual position and make sure that we get into a port within a certain range of miles, right? We're okay. We can do that. So that's fine. We can do that.
Oh, I mean, you were saying earlier how, like, for 250 years or so, that these are known zeniths, right? You have the exact timings, etc.
They're known GPs is probably the best phrase.
Well, a known GP is correlates to a time as well, right? That time correlates to an angle depending on where you are, geographically speaking, right? So in all cases, it is a conceptual model, right? The conceptual model is the celestial sphere, right? And what you're doing is you're basically equivocating the celestial sphere to the surface of the Earth, saying, well, because the sky appears to us like a sphere and we use it like a sphere, that means the ground must be a sphere. That would be a equivocation fallacy.
Well, yeah, and tell you what, how about flat earthers? You've had 150 years. How about flat earthers say, screw this globe-based celestial navigation stuff. Let's go do and apply flat Earth geometry. And of course, that's what I'm here for. I'm here to learn from the leaders of flat Earth how to apply the geometry of flat Earth. And specifically, the topic I wanted to come here was to get the geometry of flat Earth for the dip of the horizon. But if you want to talk about the geometry of flat Earth for the angle to a star, I'm all for it. So, you know, when you're at 20 degrees latitude, right? 20 degrees north latitude. What is the geometry of the angle? You measure an angle to a star, and now how far do you know you are from the GP of that star? And of course you wouldn't want to use, just to be clear, you would never use the position of the stars in a celestial sphere. That'd be ridiculous, because you don't think it is a celestial sphere. You think it's a dome or a plane or something that's appropriate for a flat Earth. So what is that geometry?
No, be asked to please clarify.
Yeah, go ahead, bro. Yeah.
So, to be clear, the celestial sphere model is still used in the way that celestial navigation is used in a planar assumption. It's because the celestial sphere is deemed to be viewed in a personal way, but it's not deemed to be something that correlates to a ground shape. Everyone can still use the celestial sphere model. That's kind of what he's saying. In terms of the angles to the stars, though, you said something earlier. You can use a star that's 1 degree if you want. Things that are below 20, but you just have to make sure you make the proper refraction corrections. Now, when you do that, are you talking about, because you said this has been done for 200 something years, are you talking about just Snell's law, terrestrial refraction, temperature and pressure corrections, or are you talking about celestial refraction? Are you talking about both?
Well, it's all Snell's law.
Well,
yeah,
you
Snell's
might
law
say that
is the underlying law for all of them.
Well, that's the claim, right? That's the claim. I don't agree with that personally, but I think that the first case is definitely Snell's law, because when you use first principles of physics to derive it, you can actually just use a formula based purely on temperature and pressure gradient and get the refraction coefficient. But celestial refraction is not the case at all. Have you looked much into where celestial refraction came from or how it was implemented into celestial navigation?
I mean, as soon as you started talking, you went right. You veered absolutely away from flat Earth as fast as you could. I'm here to learn. I'm here to learn how flat Earth geometry works. That's what I'm here for. So you're going off talking about other topics. Tell me how flat Earth geometry works.
You're pretending that a celestial sphere conceptual model is mutually exclusive to a
throw it away. Throw away
shape.
Whatever I've said.
Why would you
just
away?
Tell me. You just tell me how flat Earth geometry works for this topic. That's all I need.
We're not throwing it away. You still see in a hemispheric grid of vision.
Throw away everything I've said. Throw away everything I've said. Okay. And instead start from zero, and you tell me, how does flat Earth geometry apply to the dip of the horizon, or in this instance, the angle to a star?
So just to be clear, in your model, I'm going to compare the two.
I don't care about my model. I only want to hear about your model.
Please stop interrupting me and allow me to speak.
It is embarrassing.
So when you have your model and we have our model, right? You're telling me to throw everything away. I don't need to start from scratch and invent a new astronomical system, because back when the Chinese and the Japanese and these ancient civilizations were using celestial navigation, they were doing it under planar assumptions for thousands of years. And I've
never seen this. That's an absolute lie. Nobody has ever this geometry.
Never once. You should go look at Alan's recent presentation on the Chinese and their celestial
geometry
sphere model. They had a celestial sphere model over a topographical plane. They had their own system of latitude and longitude, completely separate from Greenwich, completely separate from the Europeans. They mapped out the South down to a certain latitude. They did all this crazy stuff that Europeans thought they were the only ones able to do, and they did it all without any knowledge of the European astronomical system until the Jesuits came in around the 1600s. But anyways, not trying to diverge into all that, just talking back about celestial navigation. If you, in your model, believe that there's truly a one-to-one linear relationship everywhere, in all the nautical miles per degree motion of the stars across the sky, and that it doesn't change, then that leaves you in a position where when we view that it doesn't actually happen that way in reality, you have to account for those differences using a phenomenon that you post hoc rationalize and name celestial refraction. This is why I was bringing it up, because terrestrial refraction, real refraction, Snell's law, is based on first principles of physics using equations relating temperature and pressure gradients to your local atmosphere. When you do celestial refraction, if you go look at the formulas, go look it up, fact check me. These formulas for celestial refraction, when you break them down individually, I'm not talking, there are formulas that combine both together and you gloss over it because you don't actually see what's happening. When you actually do it individually, first terrestrial and then celestial, the celestial refraction formulas do not involve any physical variables. The only variable involved is the apparent angle. And then it has, a second order, actually 2 second order polynomials in a giant fraction that are combined together, multiplied into those angles in order to modify those angles to get the quote unquote proper angle. And there are different celestial refraction formulas for each preferred angle band. Some people have given generalized formulas that are generally accurate for most angles, but in order to be, well within the high accuracy range, you have to have different celestial refraction coefficient formulas for different angle bands. And what this is indicative of, from a scientific viewpoint, scientific lens, if you're a scientist, you would, this would make sense to you. I'm not saying you're not. I don't know your background, right? I'm just saying this, but is that this is something that does not have a general form solution. It actually has specifically an empirical solution. We've got random coefficients like 8.314x to the x squared plus 2.175x plus 2.13, and x is the angle. And it's just random numbers. Those numbers came from where they came from. When you look at the history, how this was come up with, they went out, they had the globular geometry, they accounted for terrestrial refraction, real refraction, Snell's law. And they said, okay, here's the angle we predict to see when we measure all these stars. They wouldn't measure all the stars. They found out, hey, the ones that are closer to the horizon are actually off, and the closer to the horizon we get, the more wildly off we are. And so what they did is they said, well, there's nothing left to correct for this. There must be some other phenomenon happening. What we're going to do is we're going to take our curve of our prediction for the angles, then we're going to take our curve of our measurement for the angles. We see that these two curves do not overlap. So we're going to take the difference between these two curves, and then we're going to turn that into a second order polynomial, and that is going to be our correction factor. That's going to be our celestial refraction correction formula for the apparent angle to the true angle. And that's how they came up with it. It is literally a post hoc rescue device, turning their error into a correction in order to be able to actually predict accurate angles in the sky. Now we could do that. We could do that.
Angles. Hold on. And the angles were accurate.
Yeah. Did you hear? Did you understand what I said? That's what an empirical fix is.
Okay. So they used the globe to generate this formula, and this formula works. What you're saying?
That's not what I said. They used the globe to generate their predictions using geometry plus refraction. Their predictions did not match reality, and so then they had to error fix their predictions by plotting the real measurements against the predictions, taking the difference and turning that into a second order polynomial correction.
Okay.
And that's the celestial refraction formula. So that would be like, let me give you, like, by way of analogy, the equivalent would be like if I was to give you a math test, right? And you were, doing this math test, and every single time that you give me an answer, your answers were off by like a few percent or a few tenths of a percent or whatever. And I said, you know what? I'm gonna take the average of all your answers, compare it to my actual correct answers, and then take the difference between these two data sets and turn it into a second order polynomial. That way we, on average, correct all of them really close to the correct answer. So every time I take one of your answers, I'm going to plug and chug it into this formula, and then compare it to the true answer and see how much closer it gets. That wouldn't be doing anything scientific. That would just be saying you are wrong, but we need you to be right. So here's how I transform your answer to be correct. It's an empirical fix. It's not a general solution. It's not based on physical variables. It's all based on apparent angles and random coefficients that are arbitrary, generated from real measurements that were not matching predictions. So that's the history of celestial refraction.
Too.
Yeah, that's the history of celestial refraction.
Okay. All right. So that's all right. Got it. So now, what is the geometry for flat Earth?
What do you geometry of what?
I'm here to learn the geometry for flat Earth for initially the dip of the horizon, but now the topic has been by request expanded to. No. So let me finish. Now, by extension, the geometry for the position of the stars for flat Earth. So I haven't assumed anything. I have not loaded into. I have not loaded into this any of my. Right, I did the dip of the horizon based on 150 years of literature of flat Earth. But if it's wrong, throw it out and correct me on it. And I have nothing at all for the geometry of flat Earth for the position of stars.
Why would it be any different than what we currently use? We don't see in Euclidean space.
We do see in Euclidean space.
So railroad track lines don't converge together apparently as they get away from you.
That is Euclidean. Yep.
What?
We can apply the law. It's 100% Euclidean. The law of perspective is pretty simple. If you know how far away is the track, we know its angular size, and that's the angular separation between them. That's 100% Euclidean.
That's specifically not.
That specifically is Euclidean. And you joked about giving me a math test. My goodness. Oh my goodness.
Space is Euclidean. I'm saying we don't see that way.
We absolutely 100% see in Euclidean. Yeah.
So parallel lines can converge and diverge in Euclidean space?
No. When something's farther away from you, it has a smaller angular size. That's Euclidean. I don't know what.
Okay, so things that are parallel right beneath your feet appear to touch when they reach the horizon. How is that Euclidean?
They don't actually touch.
Exactly.
I know they don't.
Yeah.
But apparently they do. That's why you see differently than what's physically there.
Yeah, this is ridiculous. Angular size is a thing, and saying we don't see in Euclidean space is absolutely ridiculous.
Well, okay, here's this is why. So if you look at the
100% do this is a ridiculous claim.
Okay,
that
so
no sensible person actually believes.
So you already believe it. You already believe this. You just don't realize it. So when we talk about angles and viewing angles to objects, in the sky and as they approach the horizon, remember how we were talking about the star angles between 20 and 70, roughly somewhere in there is mostly linear. And as you taper off below 20 and get closer to 0, it actually goes from linear to, I think it's hyperbolic on that end.
It does not go hyperbolic.
It's either hyperbolic or parabolic. I'd have to look it back up. It's been a minute since I looked at the chart. But anyways, it's not straight. It's a straight line in the middle portion. There's a linear portion in the middle of the curve, and then it kind of curves down as it gets closer to 0. It's not linear in that region. So
it's not linear in the middle either.
It's roughly linear through the fattest part of the middle.
It's not linear. It's parabolic, and that portion of the parabola is not curved a lot, but it's still not linear.
Okay, so you're agreeing then
degrees per hour, though, right? That's the relationship, though.
But here's the point. He's agreeing, like he's arguing that we definitely see in Euclidean space, and all this is just a linear relationship, and it's just the law of, or it's just a angular size at work. But actually, we don't see in Euclidean space, because if it was true, that relationship would be linear everywhere. The fact that it scales with angle shows that it's not Euclidean the way we see it.
No. It is linear everywhere, but that is being modified by something else. It's not our vision that's not seeing it linearly. It's the effects in the air that is causing it to be a parabolic relationship.
It's not atmosphere that does it.
I mean,
but we still see
though.
It is it's not semantics at all, and is 100% the atmosphere doing it.
Yeah, but the same thing happens in simulators. You're still perceiving the thing in a non-Euclidean way. For example, if I see an airplane travel towards a mountain that's on the horizon, for example, and I'm pointing to it, it goes overhead. I'm still pointing to it, right? So it's going down, right? It appears to me, my eyes, that it's going down in angle towards the convergence point in the center, but in reality, we know that that plane is actually 30,000 feet in the sky. It's not actually converging with the mountaintop. Neither is the clouds actually converging with the mountaintop. That's just how it appears to our eyes. So that means we see in non-Euclidean space.
No, what you've just described is Euclidean inverse tangent relationship.
Inverse tangent relationship.
That's what you've just described as a Euclidean inverse tangent geometry.
Yeah, but getting off of just the general things converging into the distance, like the angle that you just acknowledged, that it's not linear, right? The relationship of distance to angle scaling is not linear throughout the entire
because
region.
of the effects in the air.
No,
not
it happens
because
in
of
simulators the same way it does with the human eye, and there's no atmospheric corrections in the simulators.
What simulators?
Any type of simulator in which you correctly model the
Any
way
type.
that
I'm not going to accept any type of simulator. I'm going to need to have something very specific. Any type of simulator is nothing. That's nothing.
Did you say that you had the paper with the curve on it?
That which is asserted with no evidence is dismissed with no evidence.
Okay, did you say you had that paper with the curves on, or which paper were you sharing?
Oh, I actually found it's a paper that shows that they've actually tabulated all of each minute of arc from 0 to 90, and they basically say they solved the 3 independent variables in every spherical triangle. It was 157,464,000,000 separate spherical triangles, which at a rate of 1,000 triangles computed a day would take some 400,000 years to compute and complete, etc. But they basically go over that there is an entire volume set, like 264 pages, or about 2,400 pages for the entire set of tables, and involves the solution of over 10 million separate spherical triangles. All of these spherical triangles are just calculated based off of, if I see a star at this angle, then this is the amount of refraction that I'm going to use in my coefficient. It has nothing to do with actually empirically, verifying the temperature or pressure like you do with terrestrial refraction. It's literally just a curve fit formula for when the stars appear to linger in the air longer than they're supposed to, because they're supposed to go beneath the horizon and beneath my feet, right? Because that's the concept, right? That we're on a ball Earth and that the stars are actually supposed to go beneath our feet. But instead, they actually have these celestial refraction corrections that explain the anomalies that we see at the horizon, like lingering stars and the sun, etc.
All right. So you were going to post the simulator. Instead, you talked about a different topic. Do you have the simulator? Where?
It's in the live stream stage side chat. You know the side chat there. And then it is at it's at 10 o'clock. Oh, so it's at the hour, literally at the hour.
Oh, you're talking about the paper reference.
Yeah, from when we were talking about.
No, but
how it's literally just a conceptual model, and that celestial refraction is not it's not actual science.
But he was saying in a simulator that because we were talking about and it was denied that the stars change elevation because it's nonlinear because of air, and it was denied that was the case. So and there's a simulator, and in simulators it's all right. Where is this simulator, and where was it done? And with no air, apparently in a vacuum, right? Where was this done?
All right. Real quick, I don't have a simulator in my pocket to pull out for you, so I'll ask you a counterpoint question. Right? I'll acknowledge that, and I'll ask you this: if you say that we do see in Euclidean space, but there's an atmosphere that makes our vision non-Euclidean, then how do you differentiate between those two statements in reality?
It doesn't make it non-Euclidean either. It makes the relationship between the location of the star in the non-refracted version and the refracted version non-linear. It makes it parabolic.
Okay, so
It's
the way
still
we
Euclidean.
see
Euclidean and parabolic at the same time. Euclidean,
what?
parabolas are part of Euclidean geometry. Maybe you didn't know that.
Okay, so
That's why it's funny when you talked about giving me a math test. Apparently, you don't know that parabolas are part of Euclidean geometry.
So you're telling me real quick.
Amazing.
So you're telling me that we not only do we exist in Euclidean space, which is fine, but we also see in Euclidean space. But then
Yes,
when pointed
100%.
when pointed out that the distance to angle relationship is not linear across the entire range of angles, but goes hyperbolic, linear, parabolic, that
Never hyperbolic. Why are you saying hyperbolic? The stars are not hyperbolic.
it's parabolic at one end and it's a different trend at the other. I need to look at the graph. Like I said, it's been a second since I've looked at the chart, but either way, it's linear in the middle and non-linear at both ends. And you're saying that is still Euclidean, even though it's non-linear.
Yes, it's still still Euclidean.
So hold on. So not having a 1-to-1 scale across the entire range of angles is somehow still Euclidean.
We see in Euclidean, but the positions of it have been modified by external factors to be nonlinear. But it's still Euclidean.
So then we don't see it as linear, which would mean we don't see it as Euclidean.
Oh, then you guys agree.
Parabolas are Euclidean.
Oh my God.
Why is this so confusing to you?
It's not confusing to me, bro. You're trying to play a word
confusing
game right now.
No, you are saying, because you've heard so many times that we see in non-Euclidean space, so many times that you don't even understand what that means. Right? You want to think that that's the case, but you don't understand the topic. You couldn't give me a math test. You don't understand this topic. You don't understand a parabola. A parabola is part of Euclidean geometry.
So
how did you not know that?
So Euclidean geometry uses straight lines. Just like let's just start with that.
It uses all sorts of lines. Y equals x squared is a Euclidean formula.
Got it. So
and that's a parabola.
Got it. So if you have 2 points, right, and then we add a third point, and we add a fourth point, and then we set these points such that the distance between them is equal, and then we check the way that the angle to these points changes as the distance increases. In Euclidean space, we would expect that the angle would change equally from point to point, just as the distance changes equally.
I'd like to correct McToon
What the
real
hell
quick.
is that?
Yo, dude, it literally says on Wikipedia even that hyperbolic geometry is self-consistent non-Euclidean.
Yes, you're right, but we're not talking about that.
Oh, so you're wrong.
Do you know what hyperbolic geometry is? Tell me what that is.
Yeah, it's non-Euclidean.
No, that is.
Okay, well, you're just incorrect.
What is it specifically? Of course, yes. Yes. B is not A. How is B not A? Because it's not A. I'm asking you, what is it that makes hyperbolic geometry hyperbolic, distinct from Euclidean geometry? Don't help them, Jesse. Don't help them. What is it that makes? They'll never get it because they don't know this topic. What makes hyperbolic geometry distinct from Euclidean geometry? Gleam knows, but I don't think he's here anymore. He would correct
Does it
you guys.
have anything to do with, let me guess, quadratic formula?
No.
Mm-hmm.
It does not.
What is it?
I'm not telling you. I'm just going to let you be ignorant.
Yeah, okay. You're the one that said the hyperbolic hyperbola is part of Euclidean geometry. That's literally incorrect.
A hyperbola is part of Euclidean geometry. Hyperbolic. Oh my gosh.
Is a hyperbola hyperbolic?
Oh my gosh. Hyperbolic geometry is a different type of geometry. You can do you can do them in Oh my gosh. This is so weird. You guys, you can still do them in Euclidean geometry. There's Euclidean geometry, There's spherical geometry, there's hyperbolic geometry. Those all have distinctions from each other in the axioms. That's all I'm going to tell you. In Euclidean geometry, you can make a sphere. In Euclidean geometry, you can make a hyperbola. In hyperbolic geometry, you can make a straight line. In spherical geometry, you can make a straight line. You think that just using a hyperbola means you're using hyperbolic geometry. That's how far you guys are from understanding this topic. That's ridiculous.
Are you done bloviating now?
So
or
real
are you
quick,
gonna-
real quick.
Wow.
Let's just check real quick. Right, I've got a railroad track, and I've got some point. I've got some point on 5 feet away from it. Okay, if I was to trace a second line through that point, or a series of lines through that point, I'm not going to say the number. How many different lines could I trace through that second point that would not intersect the railroad track?
Oh my gosh. You're doubling down. All right. Roland My Boulder said, I love this. Hyperbolic geometry is just geometry that has been grotesquely exaggerated for literary effect. And Roland My Boulder is more correct on that tongue-in-cheek answer than you guys are.
Why are you completely
On what
ignoring what I just
hyperbolic
said?
geometry is? Because all you've done is demonstrate that you don't even understand the difference between Euclidean geometry and hyperbolic geometry.
I asked you a question about lines and points. How am I demonstrating I don't understand something?
I wasn't even paying
post this
attention.
for
Ask
the
it
audience.
again. Ask it again.
I'm gonna let the audience think for themselves rather than listen to you, because literally it says right here, in non-Euclidean geometry, elliptic geometry, hyperbolic geometry, three-dimensional non-Euclidean geometry, hyperbolic geometry. It's literally right there. Non-Euclidean.
Yes. Yeah, you're right. Hyperbolic geometry is non-Euclidean, but you can make a hyperbola in Euclidean geometry. You don't seem to know this. Do you know that that's possible?
Yeah, well, parabola or a hyperbola. Let me see. A hyperbola is that hyperbolic is when I can't think off the top of my head. I'll look it up.
Can we get back to the original topic of flat Earth geometry?
This is the topic.
That'll never happen.
Well, the point is that we see in curved visual space. And
No, we don't. We do not see it. We absolutely do not see in curved visual space.
Yeah,
that is not how our vision works.
So you have an eyeball, right? And this eyeball is round, and the cones and rods in the retina in your eyeball have curvature to them, and the light coming into the center is seen coming in a straight line, and the light not perfectly in the center go around towards the edges has curvature to it as it comes into the lens, and this induces a curvature to the visual space in which we see, which our brain processes and gives us an image. We agree that space itself is Euclidean. We're disagreeing about the way that that's translated into our sight and the way that our brain is able to process the information coming in and translating that into an image in our mind. We know that you can have Euclidean geometry that can create conic sections and all these different intersections between a plane and these curves, right? Which any kind of curve traced on a plane will make some kind of different shape of a cone, but that's not the point, because the point is if it's truly Euclidean, this goes back to the line and point question I asked you. If I have a railroad track, and I have a point 5 feet away, in Euclidean geometry, by definition, there's only one possible line that I can trace through that point off to the side that will not intersect that railroad track. It's based on the definition of parallel, right? And so when we talk about parallel lines in Euclidean space, then there's no way for you to say that I see with this curvature around the edges of my vision at extreme angles around my peripheral vision, or extreme angles close to the horizon where everything converges and my brain has to process it out, that's still truly Euclidean in the regime in which we see, if it does and has those nonlinear effects because Euclidean is linear.
Euclidean is not linear. Oh my gosh. That's your problem. You think that you can only do linear things in Euclidean geometry, and that's completely wrong.
I didn't say you can only do linear things. It's that the scaling, right? If you have a geometric system, whether it's, a parabola, a hyperbola, draw triangles, draw whatever, man, like any kind of just whatever geometry you want to talk about. If your geometry does not satisfy the law of parallelism, that, the thing I said about the line and the point, or whatever that's named, I don't know if there's a term for it, but the parallel point that I made, if it doesn't satisfy this parallel law, then it's not Euclidean. Okay? It either satisfies it and it's Euclidean, or it doesn't satisfy it and it's not. There's all kinds of stuff getting into, visual space geometry and high level studies on it that, none of us have memorized off the top of our heads, but I know that one to be definitely true. If you can't satisfy the parallel postulate, then something cannot be Euclidean.
All right. So none of that matters because we can measure angles with things other than our eyeballs, and they are still Euclidean.
Well, I think there's a happy medium. I'm actually reading this. I've been reading it. I'm only on page like 30 of it so far, but it's Paul Wagner's The Geometries of Visual Space. And what he, one of the paragraphs that I just read is that that is distance and angle relations in sufficiently small local regions of the space are essentially Euclidean. On the macro level, however, straight lines in physical space may appear curved in visual space.
What was the name of Paul Wagner? Paul Wagner what?
I posted it in the side chat from 2012. Paul Wagner.
What was the name of it again?
Sorry, not Paul Wagner. Mark Wagner.
Okay.
Yeah, Mark Wagner, The Geometries of Visual Space. I think it's a very good book to have. But in order for the sake of argument, do you think we can just agree that it appears to be non-Euclidean on the macro scale?
No. Because this is the you were talking about human perception here in these things. Well, I'm not talking about human perception. I'm measuring angles with instruments, not human eyeballs, right? In Antarctica, Whitsitt thought that he was being smart, and he was saying, "Oh, the sun is, the globe predicts that the sun's only 34 degrees high, and it's definitely higher than 34 degrees." And then I got the theodolite out on my phone, measured the angle, it was 29 degrees. And I'm like, I don't care, about your eyeball measurement. I use an instrument. So I don't use eyeballs. I use instruments to measure these things. So I don't care about the spherical shape of our eyeball. It doesn't affect the instrument that's doing the measuring. And the visual space things that you're talking about in the papers when you're talking about the human perception, which may or may not be the one you're talking about here. The human perception ones are the standard that they're using, the tool that they're using to determine the distances in these human perception ones is a theodolite. They're using an instrument. This is the same instrument that I think is a great instrument to measure these angles, to measure the angles and the distances. So that is the
using
standard.
Your eyes to aim your instrument. Come on, dude.
No, you can. No, come on. Theodolites are modern theodolites don't even use eyeballs. You don't have to. You can just put a target on it and it'll measure it.
You can't completely separate yourself from human perception, dude. That's how you take measurements.
That's actually the point. Is what we have. I put it in the chat. I put it in the chat in the side chat. So just if you look at that, right?
Let me call up.
Go ahead. Sorry,
what's her name? What's her name to tell her that the sea turtles are safe because all the straws have been grasped.
Can I get a mic check?
Loud and clear, Rick.
Holy dooly. Yeah, grasping at straws, right, McToon?
What's that?
Just checking you can hear me.
I can. And I know that you're a flatty.
Fantastic. Yeah, you've identified correctly. Well done. Okay. So I've been spending about 15 minutes trying to work out what the hell's going wrong here. I don't want to sidetrack. You guys are on something now. You've kind of moved on a little bit from what you're talking about. I'm sure we're going to circle back around on it. But I don't know. When you guys have got space, I'd be kind of
You're breaking up, Rixky.
I think he said when we've got space, he wants to come back and touch on something, but he didn't get to finish the sentence. What heard, Rixky?
NASA must have taken him out because they knew he was going to share the woke truth of flat Earth.
Yo,
in the
McToon,
outback.
did you see what I posted in the side chat a minute ago? 1 minute ago.
I'm not watching the side chat, just so you know. So
why?
I have live stream 1 text up because this is what's broadcasting over to YouTube.
Okay, I'll put it in the live stream
Okay.
text. I got it. I'll put it in the live stream text.
Same here. I'll put the things that I actually post. I post in the wrong spot then for you. My bad.
Ultimately, the reason our visual perception feels non-Euclidean is due to how the brain interprets the visual signals coming from our eyes. While the physical world is Euclidean, our visual system processes the 3D world in a way that introduces distortions. The curvature of the retina causes distortions in peripheral vision. The perspective effect causes parallel lines to appear to converge. The field of view stretches and compresses space in ways that do not match Euclidean geometry. These effects combine to make the world feel like it's not perfectly flat in our perception, even though the world is Euclidean in reality. Conclusion: visual space is not Euclidean. So you're correct in saying that visual space is not Euclidean, but that's because of the distortions and perceptual effects in how our brains process the information from our eyes. The physical world is still Euclidean, but our perceptual experience of that world can introduce distortions that make it feel curved or non-Euclidean, especially in our peripheral vision.
I thought relativity is non-Euclidean.
So,
completely different topic. Thanks for sidetracking.
Once again, as I said earlier, when you combine the fact that we have curved eyeballs and parts in our eyes that have curvature to them with the way our brain interpolates and processes the visual data coming from them, that's how we end up with curved visual space. We know that space is Euclidean, but we don't see it in perfectly Euclidean ways. And this is like,
but so that 100% supports my point. We don't use our eyeballs to do the measurements. So the human perception isn't a thing. It feels isn't a factor. I don't care about how it feels. Don't use your eyeballs as the device of measurement. Use a theodolite or a sextant.
Can we get a definition of Euclidean? My perception at the moment, as far as that's concerned, is if you point a gun at it and you've got a ballistic projectile and you shoot at it, presuming that projectile goes exactly straight, that is Euclidean. If it's bending at any other point,
that's linear is the word you're looking for there. A straight line. Euclidean geometry is geometry that satisfies the 5 particular axioms of Euclidean geometry. Hyperbolic and other geometries don't satisfy those 5. They have different, particularly the 5th of those 5 axioms are different.
So isn't it the case of was it Einsteinian sort of like observing Mercury from behind the sun? Is that still Euclidean in your interpretation?
That's about the curving of space-time.
So that's not Euclidean anymore, isn't it? Which is what Gatebreaker was trying to bring up a little bit before.
Exactly.
Which is what I'm trying to say. Is like Euclidean is that you point a line at an object, you're going to hit it. If it starts bending, right? If the light is bending, your projectile, your ballistic thing, it doesn't behave like light anymore. Therefore, you won't hit it because it's like the fish in like trying to shoot a fish in the pond, right? That's non-Euclidean at that point. It's the object is moved from its field of view.
It's just not straight lines. That's all you're talking about.
But now we should be able to move past this because there was a hang up about whether we see in a way that's non-Euclidean, and we found out that we do.
But we could also, but
we
don't.
You do so long as there's no refraction going on.
What?
If the light is bending, it's no longer Euclidean because your perception is being warped.
It's still Euclidean just because it doesn't take a straight line.
Okay,
non-straight lines exist in Euclidean space.
Euclidean. Okay,
it's still Euclidean. It's still 100% Euclidean.
You're not perceiving in Euclidean anymore, then.
Oh my gosh. How
Rick,
can
go
you
ahead,
guys
Jesse.
not understand this at all and talk like
Because
you're
you've got
smart?
to understand the
You-
path of
you
light
guys are
at that
just
point, Jesse.
you guys are just like sitting here all day and nobody comes in and says, "Wait a second, guys, that's not right." How many days have you guys sat around
Dude, this is a
patting
semantical
yourselves on the
argument at
back?
this point. This is a
No, it's not
semantical argument that you're
semantic.
coming in with
No,
different,
and you guys are
a
just
different
patting yourselves on the
interpretation.
back saying, "Hey guys, that's
Dude, this is
non-Euclidean
not your
geometry."
chance to bloody.
It
No, no.
100% is Euclidean geometry, and you guys just don't even understand this topic. It's ridiculous.
Relativity is non-Euclidean.
But we're not
Thank
talking
you.
about relativity. Why?
That's space. That's space. That's the reality. It's non-Euclidean.
And using Tide for clothes detergent is not using cheer for clothes detergent. Who cares? It's off topic.
What? How's it off topic? It's space. Space time. World we're in. Is it non-Euclidean?
We're not talking
Dude,
about
literally that means that light is refracting due to space-time being warped by mass. Like
oh my
mass
gosh, not
changes
at all.
the-
No, it's not refraction.
That's
not
why
refraction.
you can see around it, dude.
How do you not understand that's not refraction? Oh my
No,
gosh.
you're augmenting Euclidean geometry
It's
using
not
refraction.
refraction. It's not refraction. How are you so confused? It's the bending of spacetime.
Which is non-Euclidean.
Correct, but it's
perceiving the
not
star?
refraction. But it's not refraction.
Do you think the star at the
get it.
horizon is exactly in the line of where you're looking?
Crap, you think you don't even you
It's not, is it?
you actually like
not.
are here top
No,
lefting
no.
this
Don't,
whole
don't,
thing.
don't. I don't want to hear your incredulity, Biasticles. You have something to offer?
This isn't incredulity. This is you.
This is incredulity,
not
pure
even,
incredulity,
Not
sir.
even knowing that the general relativity and the warping of spacetime is not refraction, and you don't even understand that. That's embarrassing.
Okay, will you see light or from an object coming in at a different angle due to what is it? The bending and warping of space-time.
Yes, but it's not refraction.
Thank you.
Okay, so back to topic though, real quick. Like just to confirm, like real quick, I was going to say to you, Ricky, like Euclidean space is essentially just a XYZ grid, right? Just think of like a cube, like a cubic XYZ grid.
You can use different coordinate systems in that as well.
Okay, but it's the way that we think about space in general. Like we think of this flat grid. That's Euclidean space. Now,
no,
dude, I don't want to go through all 5 postulates. That's the simplest way to describe it, bro. I'm trying to get off of it. Okay. Now, anyways, back to the topic though, right? Well, like I'm trying to circle back because we got 2 different rabbit holes. It took forever. We were relating all of this to the way that we see because we were talking about angles to stars, and we were tying it all into the way that there's a nonlinear relationship throughout the motion of the stars across the sky, and how they have to incorporate post hoc rationalized quote unquote corrections that they call celestial refraction in order to actually make accurate predictions. And I explained where celestial refraction came from and how it actually works, and how it's not actually a physical effect from any general formula or first principles, but it's actually an empirical hotfix, a curve fit formula. And so knowing that, how does that at all change the way that you think about the way that, celestial navigation occurs, the way that visual space works, the way that 69 miles per degree or 60 nautical miles per degree works when it comes to stars? Because why would they need to incorporate this post hoc hotfix onto what should already be corrected, what should already be accurate? Why is it that there's all this crazy empirical curve fitting that has to happen in order to make the predictions work? Because we could do the same thing.
You could go ahead. Why haven't you?
No, okay, so here's the process. If I was to say, I'm going to use plane trig to predict all these angles to the stars. I'm going to use the celestial sphere model, but I'm going to just use plane trig and terrestrial refraction, and I'm going to get a set of predictions. When I go and measure them, they will be a little bit off. And then I'm going to say, okay, so I'm just going to take the difference between my measurements and my predictions and spit out a second order polynomial, and that's my correction factor. Here we go. I'm going to call it flat celestial correction, flat celestial refraction. you would never accept that as a real scientific process. You would say, look, dude, you were wrong. You invented this magic formula to fix all your numbers so they look right, but really you didn't know what you were doing. That's what you would say to me. But that's literally what the glob is doing with celestial refraction.
So I've seen many people attempt this because I have a $10,000 challenge to do this exact thing. And every time they do what you just said, they use the globe to do it. You have to use somewhere. You have to hide in it. You have to embed it somewhere. You have to use the radius of the globe in order to do that fitting.
Hey, Toon?
Do it without the globe. Good
Your
luck.
radial field of vision. It's your radial field of vision. I think I can go at a slightly different tact here. And I don't know, Piezo, I don't want to interrupt your train of thought either. It's up to you, mate.
No, I mean, I'll let you talk, man. That's fine. I'm pretty much done. I just what he said that.
What's your name? What's your
Sorry?
actual? What did he call you?
Piezo.
Piezo.
Piezo is what he called me.
He alternatively goes by Piezo. My apologies. Jesus Christ.
Okay.
It's a yeah.
Call me that. That's my screen name. But yeah, you can call me Piezo. So I don't have to go by Jesus Christ.
My apologies.
I'm not Jesus Christ, right? But
How do I defer or refer to you? My apologies.
you can just call me
I
Piezo.
didn't
Bro,
realize
that's
your
fine.
name.
You know I
Yeah,
go by
cool.
that. But
Sweet, done.
no,
Hey,
but
Toon?
he made a claim.
If you're looking to get out of the loop you're in, I see Plain Reality is on stage, and he has quite some different ideas about the Flat Earth prediction for angles. So you might call on him.
Okay. Well,
Cool.
Before we do that, I want to make sure that I don't cut off because the question to everybody here is, first, what is the correct flat Earth geometry for the dip of the horizon? And second, then, what is the correct flat Earth geometry for the angular elevation to stars? And so far, it's been
Can I have a crack?
all you want to talk about is the globe. So I'll say yes, you can have a crack with one caveat. You can only talk about flat Earth.
Sure. So we've got two horizontal planes, that of the ground and that of the sky, right?
Okay.
Cool. We're going to embed the star in the sky, and the observer is only sitting at the ground.
Okay.
We're going to recognize that there is a gradient, a refractive index caused by the medium we're within, right?
What is the direction of the variation of the index of refraction? So like where is the index of refraction highest and where is it lowest? That confuses
it bends down towards the denser medium, and the denser medium is at the ground.
Denser medium at ground. Okay.
Cool. So same formulation. It's basically reality I'm trying to describe. What we have to defer to is, well, actually, I won't do that. I'm only going to talk about flat Earth as you actually requested, right? So
yeah.
I'm not going to worry about you as the observer. I'm going to worry about the field of influence of the star in the sky, right? That's on that horizontal plane above, right?
Okay.
Cool.
Field
So
of
if you've got light,
wait, what's the field of influence of the star?
Yeah, so this is the what I've referred to is like it creates an umbrella effect. So I'm not too worried about the observer. I'm only worried about where that star can be observed upon on that two horizontal planes, one above the other. The star is embedded in the upper, and we've got the gradient and a refractive index occurring throughout the course of it to perceive it down upon the ground. That source of light in the sky is going to create an umbrella. If you cut a section through it, you could draw it out as an umbrella. Do you understand the shape that I'm referring to here?
The star, the field of
so the perception of that star, if you wanted to draw out, you know that the light is bending towards the denser medium. So you've got a source of light really high up, and you know that the source of that light is bending towards the denser medium.
Okay.
As a consequence, the source of that light, as it emits The only way that it could be perceived, you would articulate this upon the surface, an umbrella effect. It would sort of cast itself down. The light would be traveling horizontally out. As it enters into the denser medium, it goes down, and then it starts falling into the ground because of that denser medium refraction, right?
Okay.
That's the cause of why you have a limitation of your field of view on with two horizontal planes, one observer on the ground where we all are, and the source of light above. That's why the field of view cuts off.
Wait, I want to make
That's
sure
why you think
I was taking notes. You said the denser medium is near the ground.
Mm-hmm.
Okay, so that will cause the light to bend toward the ground, right?
Yeah. We're talking about reality.
Okay. Yeah. Yes, exactly.
So there's a field of view. That's the field of view that has been cast down upon the ground surface. You can put the observer anywhere within that umbrella that's cast of that object down upon the ground. This is why, like, talking about the observer can sometimes get confusing. I want to try to articulate that like the source of the light and how it behaves across the surface of the ground. What would happen, right, if it's an umbrella that's being cast, and that's what it would be articulated from the notion of refraction of light traveling through from a low density down to a high density. As you moved away from it, it would appear to disappear all of a sudden because that light is crashing into the ground. It can no longer be perceived.
But you said that the light bends downward
towards the denser medium. Yes.
Okay. So, but when that happens, yeah, could you maybe draw this? Can you draw a picture of this? That'd be a good idea.
Take an umbrella, take two horizontal planes.
I want you to draw
two parallel lines, right?
I can draw it,
at the
but
top,
I want you to draw it. I want to see you do the drawing instead of me do the drawing.
Dude, he's Australian. He can't draw.
I want you to.
I used to draw for a profession, my man.
I know. That's why I said that.
I just don't have the tools at hand right now. This should be like, this is so obvious to me. I don't understand why you've got a problem with it. If you take an umbrella,
trying to make an example, bro. That's why. That's
two parallel lines, one above, one below. You can draw this sectional view out, right, and then just place the umbrella, the form of an umbrella, and the tip of the umbrella is the point source of the light.
Yes.
As that light emerges from that source, it will go out, and then it will start crashing down into the ground. This is our field of view of that star. You can only perceive the star within that umbrella.
Okay, so I have on my YouTube stream here, I have a drawing of it that I'm going to show to the audience here. There's the umbrella, right? And so you're saying that if I just draw a thing, I'm on my YouTube stream. I know you can't see it on Discord.
Sure.
And sometimes I've had trouble if I share when I'm doing a live stream, if I share my screen on Discord, it crashes. So I'm a little hesitant to do it. And so you're saying within so I drew two lines and made an umbrella as you suggested there. And you're saying that within the umbrella, I should finish those all the way to the ground. Okay. So, I can let me do this. I'll take a picture of this and I'll
RG the artist would like on stage.
I just messaged him. He can go next after playing reality. And Rick.
All right. Let me drop this in here.
What are you doing right now, McToon? Sorry.
I'm gonna drop in the drawing that I made.
Based off of Rick's description?
Yeah. There we go. All right. So there's the drawing that I made. Okay. So is this what you're saying?
Look in the live streamed text.
Perfect. Yeah. Yes. Basically, that's what I'm saying.
Okay.
It won't exactly like the ultimate form of it won't be as domed like that. I suspect that it would have far more of like the shape of an umbrella, which like a little bit more horizontal in the center at the top, and then it will curve down a little bit faster on the sides. But principally speaking, that's what you've drawn it well. Thank you very much.
Okay, so now I'm going to draw an observer at the edge of the umbrella on the right. And so we've got the star at the top there and the observer there, and the observer is going to see that light come to him at a certain angle, and I'm gonna show that angle there. So this is at the edge, right? So that's what at the left side or the right side of that umbrella. That is immediately before. If the observer's right on the edge of that, that's just before it crashes to the ground, and they no longer see that star. Is that what you're saying?
Have you uploaded that image?
No. Yeah, just the picture that I did. I haven't drawn the next part yet, but I just
okay.
want to. So you're saying that if I take an observer on the left side, what's he going to see?
Yeah, if you're over on the far left-hand side, you would not perceive the star anymore.
Okay, but just inside that, where he can see it, there's a spot where he can see it. Okay,
and that's called your celestial sphere. This is your field of view, looking up into the sky.
Okay, so I'm drawing the observer at that position, and I'm highlighting then the angle. So, all right, I'll take the next picture here. And here we go. So you're saying that the observer then would see the light coming from immediately above them. That'd be at 90 degrees zenith.
Yeah, this is where we get into the issue. This is a celestial sphere. So this is why I wanted to start off with the emanation of the light, describing how it would articulate itself across the surface. Presumably, so in that umbrella, right, you could raise an elevation and it would come into your perception. But I'm going to try to, I don't want to conflate or confuse it too much. I just want to deal with those two variables. You're saying that it comes into the top of the field of the observer? That's because of the nature of the way that you've drawn that umbrella. I'm simply just using the notion of the umbrella, saying that the point source is on high. And then if you look at the way that light behaves within the field that we, sorry, I should stop using that word. Within the medium. Yeah, thanks, Biest. Then it would sort of start falling as it sort of moves away from you. So it falls away from your field of view.
So
and that's why you would see it at the horizon.
Yeah, the lines that I drew are actually the lines that the light would take according to what you've said about the gradient, the right. The refraction gradient.
No, so you've got too much arch on that umbrella. I'm simply using the notion of the umbrella, like it's not vertical at the outer extent. In fact, I would ask you a question at that point, right? How would you perceive that it would occur that star would disappear from your field of view? Would you be stating that it would disappear like right above you or something with the way that you've drawn that?
I'll update the drawing. Just a second. And I'll put the I'll have the umbrella not be so
if you took if you took a glass of water and you looked at the meniscus as the water touches the side of the glass, it's probably more akin to something like that, where it's quite horizontal at the top port, and then it will disappear as it sort of angularly moves away from you.
By the way, Rixky, feel free to tag in Plain Reality whenever you're done. I'm dropping to listening mode.
Yeah, this is my my last little foray, and Plain Reality can take the seat.
All right. So here's the updated one. So you can ignore. I move the ground up, so you can move. You can. I think it should be going. There you go. So just I move the ground up, just use that, ignore the ground that's lower there. So now we've got the observer there on the new edge of the umbrella.
Yep.
Okay. All right. And so that angle that the light is coming into the observer's eyes is at 60 degrees. It's approximate. instead of 90. Right?
Well, it is. How is it? It is coming in like that, but then this is where we get into this discussion of Euclidean versus this like sort of refraction, which we've kind of already disagreed upon.
Well, I've already applied to the refraction. The curve of the light path is due to refraction by your claim. So the light path is curving because of refraction. So we've applied refraction here. So now the observer at the edge of the umbrella should, as drawn here, should see the light coming in at a rather high angle.
Okay, imagine that star is slowly moving away from the observer. What would you expect to happen? Do you expect it to just disappear up in the middle of the sky somewhere?
You mean if we have an observer that's farther away? I want
the star. Like just as the stars move away from us, right? As they move into the west, you're observing the star. It has a field like an umbrella that I sort of articulated, and as it slowly moves away from you. So imagine it starts at your zenith, slowly moves away from you, and as it hits the horizon, it should disappear. Okay, that's its field of influence.
But this field of influence stuff isn't the laws of physics or optics or geometry. This is just I don't know what this is.
It's influential such that you can observe the actual source of light. That's all it is. I don't know. I'm just trying to say
that doesn't make any sense at all. So I'll move the star.
An area of observability then.
Okay, but I don't know. But we haven't yet determined what is causing the observer here. Right, I've got the observer here. Right, he should see. This is just like one more step away. He should then see nothing of the star, but just before he sees nothing of the star is coming into his eyeballs at 60 degrees. Right? That's applying refraction to the path of light that's coming down. Right?
Yeah, light is far more subtle than that.
So
right, the refraction index is far more subtle than.
Yeah, it's definitely not going to be. It's definitely exaggerated, but the exact degree, the exact angle doesn't matter. It's going to be some not near 0 degree. It's going to be larger than 0 by a good factor. But here I'll draw. The cat is just meowing at the door like crazy. I'm gonna draw the star farther away. So you like imagine the star is moved farther away. Rather than draw another drawing, I'll just move the observer. Okay, that's the same. So we now have another observer that's farther away, right? And then what's going to happen
outside of that umbrella.
Yep. But the thing is that the light emanating from the star emanates in all directions, and so it still gets to him. So here it is.
You don't know that. You don't know what the nature of the star is. You think that the star emanates in all directions. We don't know that. All we know is that from the ground point of view, when we look up, we see a star in the sky. As far as I'm concerned, anything else that you're seeing as far as video cameras that other people are providing you, you've never gotten above the star to actually determine whether it emanates in all different directions.
Well, I have gotten above stars because I've been in airplanes where the stars were angled down from me. So
that's a field of view, sir. That's not to say that you're above the star. You haven't looked at the star and then seen Earth in the same image or picture, have you? Like in order to do that,
of course,
that's just your globe model, dude.
No, I'm not talking about. I'm talking about flat Earth.
There's no way that you've told me that you've captured both the star and the Earth in the same image, except for in CGI.
Oh no, it's super easy. You get in an airplane, you look out the window at nighttime, and you see stars that are lower than you, right? There's an angular, a negative angle to the star from where you are. So if the Earth is flat, I'm applying flat Earth, this is not the globe. If the Earth is flat, in order for the stars to have a lower angle than you, they must be at a lower elevation than you. There's no way around this geometry. And your application here is even. It supports that same thing. If I apply the same geometry, optics, physics that you've described here, then that doesn't help either.
So I want you to
there you go.
This is where it starts getting a little bit complicated, right?
Finky is typing. Hold on. Finky is typing. Just posted a great picture. We see here.
Dude,
stars at a lower angular elevation.
When you say that you're rising up inside of that refraction index medium, right? The light changes. You can see further.
Why?
So when I talk about that umbrella, it's only specific to you as the observer looking up into the sky. If you raise up, you're no longer within the medium. You need to change that. So if you were to truly draw that section, what would happen?
But we
is
only
it
get to
actually
apply
starts-
But I'm only going to apply the known optics, physics, and geometry. I'm not going to just invent magic stuff. Right? I'm
This
not
is
going to
not
go for magic
stuff, dude. This is not magic stuff. Imagine you're rising up
so use
inside of the medium, so you're reducing your refractive index.
Okay, so then you have less refraction. It's gonna be a straighter line than a curved line. Okay,
Exactly.
That doesn't help.
So when you draw
doesn't
that
help.
umbrella shape, actually, if you get above the ground, just slightly above the ground, you would find that umbrella shape, if you're drawing a sectional line between the observer and the emittance, like the source, if you draw a sectional line through, as you rise up, you will begin to see it again because the refractive index is reduced. So now it's not having to, it's not as, like, this light source is not bending as much to get to your eye, so you can see further as a consequence. So that umbrella then actually starts,
all right,
bending up on the outer lip of it. It starts bending back up again.
All right, there's a whole bunch of problems with the geometry here, but I'll draw another one here.
Ain't no problems, man. I thought about this rather it's well resolved.
It's a beautiful example too. I appreciate that.
All right, so we've got here an airplane flying at some elevation, not to scale. Don't worry about the scale. You've got the ground at the bottom, and you've got the plane of the stars at the top. Right now, in the picture that Finky is typing, just posted. We can see out an airplane window, we can see the stars, and we can see stars at a negative angular elevation from the observer. Okay, and this happens. This is easy to see. It's not a challenge. So now we've got. I'm going to put a star up here, and now only using light that's bending downward, as you've said, and we've agreed to. How does that star that's up in that flat plane above there appear to be coming in at an angle below 0 degrees angular elevation?
Just give me a second. I'm mapping this
I don't
out.
think it's bending.
See, I think that the source of that light would almost start bending. Is it bending? No. Give me one sec. I need to start drawing this out at this point. It starts getting too complex. I appreciate that. I know that plane reality, I think I've taken it as far as I can verbally speaking. If I was in front of my computer, perhaps I could sort of continue on.
Well, try to draw some pictures. I'd love to
where we've gotten
pick it up.
Yeah, done.
All right.
Awesome. Thank you.
Can you rephrase that one time, McToon? Rephrase that how you used from the beginning, if you don't mind, please.
Rephrase this one.
RG, we're gonna let plane reality
Yeah,
get
all
in
right.
here.
Oh, go ahead. Okay.
So
Go ahead.
hey,
Oh, is he not in here?
one more time, quick. Finky posted a picture where from an airplane where you can see stars at a lower angular elevation than you, so they're below eye level, right? So in order to see them, you have to look down somewhat, and so in order to do that, I'm just asking if you've got the plane of the Earth and the plane of the stars, and he says the stars were embedded in the plane. I got the star here. How is it that the light can come into the airplane from a negative angle? And but he said that the light will bend downward, not upward. So I don't know how that's going to be possible in this model. So
We got
anyway,
plane reality here.
all right, plane reality, and then wait, plane. Oh, that's not plain truth. I was thinking of plain truth. All right.
Oh, this guy's
same
super
subject
nice.
in general, but different person.
Okay.
Hey, McToon, first up, well, I want to discuss one thing with you. I was looking for your observation that you said that you did someone's $5,000 challenge, looking at a pier from across a lake or whatever it was. I was looking for that video, but I can't find it on your.
It is on. It was from January of this year. Still this year. Let me see
Well,
if
it's
I
not in
can.
your videos.
It was a live stream, and I have a lot of live streams on my MC Toon Live channel. I think it was on there, but it could have been on my Conspiracy Tunes channel, but probably not. So let me
Right. So
just
anyway,
search for Tahoe.
so even if the Earth is a globe, you wouldn't have seen that pier anyway. Why would you not have seen that pier?
If the Earth is a globe?
Even if the Earth is a globe, there's
Yeah.
no way that you would have seen that pier anyway from your observation. Why is that? Nothing to do with the
Because-
globe. Why wouldn't
because
you
the
have seen that pier?
If the Earth is a globe, you wouldn't see it because the curve is in the way.
No, but what was it about your observation? So what were you looking at?
I
Do you
don't know what
remember
you're
your
talking about.
observation? Do you
Yeah,
remember
we
your
saw
observation?
the Calneva Resort. And the Calneva Resort, which is a couple hundred feet up the hill, was immediately above the surface of the water there.
Okay, and then what were you seeing? Was it clear? Was it a superior mirage? Was it an inferior mirage? What was
There
it?
was no miraging that I could tell, but it was certainly blurry. Now the day before, the Robinson twins went there, and we met them there on the day of as well. But they had gone before, and the conditions were much calmer. And I don't think if you probably can find. I don't know if I'm going to be able to find
can
them
you find
quickly.
it, take a screenshot and post a picture of it? Because we're about to show that you don't actually understand observation, and it was an inferior mirage. And I could see that the moment I looked at it, I saw that it was an inferior mirage. So if you're going to go out and do observations, but yet you can't even determine whether or not something is an inferior mirage, I don't think that you should be making judgments on what's going on. Because if that was an inferior mirage, which it was, there's no way whether or not the Earth is a globe or flat, it doesn't matter. There's no way you would have seen that. Now, I have on multiple occasions in multiple messages directly to you, challenged you on that $5,000 thing, saying that I will prove to you that no matter what, whether the Earth is a globe or not, you would have never seen it in the first place. And you keep dodging that. I've said it directly to you, and you've messaged me in comments, and I've messaged straight back to you directly, asking you and challenging you this $5,000 thing, and you never reply.
Okay, you are one of 100 flat earthers that is doing the exact same thing. So you're a nobody, right?
Yeah,
if
all
you
good. Yeah, you can say that,
want to put
but when
if you
you
actually want to
directly
put money
comment-
to it, hold on. If you want to put money to it, I'll listen. But if you're just
When
going to
you
be one of the
directly
anonymous
comment-
many, then you know,
when you directly
I'm not
comment
gonna.
to me, and I directly comment back to you, and then you stop replying.
Yeah, I got
when
busy
say
and
I
distracted
will
by
take
100
you up
other
on the-
people.
When I say I will take you up on the $5,000 challenge, or I said that I will put up $5,000 to prove that you're either ignorant on observation or you are lying to people.
Got it. All right. My email address is mctoon@mctoon.net. If you actually are
Well, do you
serious
wanna
about
go
that,
in-
step one would be getting your money in ready to be in escrow.
Well, it's too
Right.
late now
And
because
step
I've already
two,
just proven it. So it's
and
too
step
late now.
two would
We've already
be
gone over it. So what you can
defining the
do-
rules. Would be defining the rules and the acceptance criteria of either case.
It's too late now anyway. So what you can do is you can go in, you can find that, and you can post a picture of it here so we can all see that it was an inferior mirage. Now, if you want me to prove to you how and why you wouldn't have seen it because of the inferior mirage, then that means you're ignorant to observations. Now, what does an inferior mirage do to the horizon?
Oh, teach us, oh wise one.
No. You're the wise one. I'm asking you a question. What does an inferior mirage do to the horizon?
No, you're the one trying to make a point. Go right ahead.
So what you're saying is you don't know?
No, what I'm saying is you go ahead and make your point. I'm not going to follow. I'm not going to follow this goat rope that you're bringing me on. Just go for it. Present your case.
Okay, so we'll all just assume that you don't know what an inferior mirage does to the horizon.
No, what you should
So if
assume
we're-
is that I'm not playing your game and that you should just go and talk.
Okay.
Instead of putting
So-
words in my mouth like an asshole does.
Okay.
All right.
so
Jesse, you were wrong. He's not a nice guy. He's an asshole so far.
I'm not being an asshole. I'm just saying.
Yeah, you're 100% being an asshole. Just make your case.
So an inferior mirage brings the horizon closer to you. And when it brings the horizon closer to you, it drops the entire scenery, it drops the horizon. The horizon now appears much lower. So there's your angle dip. There is your dip. And what happens when the inferior mirage disappears? Have you ever actually watched what happens to the scenery as an inferior mirage disappears and then goes away, and now there is no inferior mirage anymore? Have you ever watched that before? Have you ever seen that process happen?
Keep going. I'm looking
Have
for
you ever
the
seen?
I'm looking for the video you requested.
Okay, but I'm asking you, have you ever seen?
I'm not answering.
that process
Make
happen?
your case. You can make your case without me, big boy.
No, I'm just asking you a question. Have you ever
If
seen
you
that
can't
process
make your
happen?
case without me, okay, fine. You need to have somebody to hold your tallywhacker while you wee. But be an adult and just go make your case.
Okay, well, I'm just asking you a basic question. Have you ever seen the conditions go from an inferior mirage to the point where there is no longer an inferior mirage? Have you ever watched that process? So you can't answer a question?
I'm not answering your questions. I'm waiting for you to make your case. I'm not
This is
following your
meant to be-
lead. Just present your case. Why
He's
can't
making
you
his
do
case.
that?
He's asking you a question, bro. He's asking you.
I do. I know that, but I don't give a damn. Make your case without asking me a question. Go ahead.
Weird.
Chop chop.
Yeah. You're refusing
He
to
doesn't
answer
want to do the
because
Socratic
clearly you don't-
method. That's obvious.
clearly you
But it's
don't
okay.
know.
Just make the argument.
Go
brother.
ahead.
Right.
Go ahead.
So as the inferior mirage disappears, you will watch everything rise up, the horizon extend and rise up as it does, and the entire scenery rise up with it. Now, you can then watch it go to the point where the horizon rises above your eye level. So during the inferior mirage, the horizon will be and can be very well below your eye level. When the inferior mirage disappears, the horizon can now rise up very well above your eye level. Now, do you know probably what is close to the highest point that personally I have seen of where an inferior mirage can be? Like, where do we
Upland.
normally get told? What does Ruhif always
What do we
say?
got?
Ruhif always
Food.
says,
He was hot mic and I got him.
yeah. So Ruhif always says, go higher. Just get up higher. You can't be down low. You got to get up higher. So he's always saying, get up to 100 feet, 200 feet, 300 feet. Well, we can go up to almost 3,000 feet and you can still see inferior mirages in the distance. So how high do we have to go to get rid of an inferior mirage? This is a question, it's almost a redundant question. I don't know the answer to that because the highest I've seen is almost 3,000 feet. So if we can get to 3,000 feet and still have inferior mirages, meaning we still have a major dip in the horizon. So how are you going to determine whether or not the dip in the horizon that you're seeing off in the distance is due to refraction or due to F-curve? Go ahead.
All right. So you completely missed the point of the observation, of the bet. The bet was some blowhard douchebag on Facebook claiming that he could zoom into the dock across all of Lake Tahoe, all 19 miles away. And I said, okay, I'll take that. I'll take that $5,000, put it in escrow, let's write it up. And he wouldn't do it. He wouldn't do it. So I'm like, fine, I'm going to shut you up. I'm going to go there and do it. Because I knew he couldn't, right? At 19 miles, you can't see it over across the globe. Whether or not you could see it for flat Earth, doesn't matter. $5,000 is what he owes me because I went there. I brought the P1000, which is the camera he was going to use. He said you could zoom right in and you could read somebody's shirt, was what he said. Ridiculous. He's never obviously used a P1000 at 19 miles and seen what you can actually resolve with it.
Let me just interrupt for a
Right?
second.
So-
I
so
agree.
that's
There's
what
no
I
way
did.
you would be able to- let me
Yes.
just agree with you for a second. There's no way you'd be able to read someone's shirt from 19 miles away.
Yeah. So, and he thought he would. That's how incredibly stupid he was. But we saw that the Cal Neva resort was very close to the horizon, and we did not see any farther down. And I'm not finding the video from the Robinson twins at the moment.
I just want to clarify.
Um,
Did you say that you would not be able to see 19 miles away because of Earth curvature?
Earth curve. Yeah, Earth
on
curve.
Earth curve.
Yeah,
Okay.
at that.
I just
At
want
that.
to.
Oh, I found their. Okay.
Okay.
I found their. So the Robinson twins, they like. Oh my goodness, they travel a lot. They like to go see arches. So let's see. And they may have a different channel. I'm gonna have to. I'll have to email them and get it. I did find their email address.
But you have this from one of your lives?
What's that?
The
I
actual
posted.
observation that you did.
I posted my video that I recorded in the chat a little bit ago.
Oh, did you? All right, I wasn't looking at the chat.
And you can look at that. Now I have another thing coming up at 10 minutes ago. I've been on here for 3 hours, so I don't want to just dip out. Right? I'm happy to come back and if you want to discuss this more. That wasn't the topic for today.
So you put it into the. No, I know that's not, but we're also talking about the dip to the horizon here. So the dip.
Yeah, I was going to actually ask you, what does that mean?
What does the dip to the horizon mean?
Like when you say, what is the dip to the horizon on a flat Earth? Doesn't it depend on your observer height?
Yeah. And so I posted, and I'll post it again.
I tagged your plane.
Did you post it, Jesse?
Yep, and I tagged him.
Okay.
Yeah, I see it,
Okay.
thanks.
So I simply applied what Rowbottom said and what flat earthers have been saying on YouTube, Facebook, X, TikTok for 10 years. Even the flatearthsociety.org forums. The dip of the horizon. And I did not include for flat earth, I did not include refraction because generally flat earthers don't include refraction.
Well, you have to include refraction because we're looking across the plane. So
I
you have to
agree,
include
and
refraction.
so that's why I came here saying, hey, what is the correct dip of the horizon from 35,000 feet predicted for flat Earth? Because it's if you say it's an infinite plane and there's no refraction, well, it's easy. The answer is 0. If it's not an infinite plane, if there's an edge to it, I don't know, is there an edge to it or not? What is there? Some say no. Some say yes. Well, what should the dip of the horizon be from an airplane at 35,000 feet? And does it matter which direction you're looking? But nobody
You make a
had any
geometrical
answer.
claim if you don't know the entirety of the
Well,
Earth.
what I'm saying as well is that if from almost 3,000 feet, we can see the refractive effects of an inferior mirage, meaning that we know 100%, because it's easy to prove, I could prove it many times over, that when there is an inferior mirage, the horizon is well below. Like there is a major dip in the horizon. So as that inferior mirage goes, and we see further, the further we see, the more the horizon, as the horizon extends, it appears to rise up. So if we can have an inferior mirage when seen from 3,000 feet, that's the furthest I've seen, which is an observation of Mount Koenigu from 770 meters, from 100 and whatever it was, 60 miles away, and there was an inferior mirage. So if we can get an inferior mirage at almost 3,000 feet, how much higher do we have to go for there to be no inferior mirage? Because like I said, Ruhiv keeps saying, go higher, go higher. Well, how high do we have to go? Now, when we're getting up to 35,000 feet, I don't think that we really have the optics to be able to look through all that atmosphere to be able to see whether or not on the horizon we see an inferior mirage. I don't think we have the optics for that, to look through that atmosphere. Maybe infrared might see through there. But how high do we have to go then for there not to be an inferior mirage? And if we can see inferior mirages, we know there's a dip in the horizon. So how are we determining whether or not that dip in the horizon is due to refraction or due to Earth curve?
Great question.
That's why I'm in here asking. Flat earthers have had all this time and yet no answers. The best I have, the best claim I have is from 150 years ago, the book Samuel Rowbottom wrote. No flat earther that I've found in the meantime has come up with anything else. And here you are saying that you got to do it this way. Well, go right ahead. This is the essence of science, making a prediction and testing it.
Yeah,
And
well,
I just pulling teeth. I can't get a flat earther to make a prediction about flat Earth. This tells us all we need to know about flat Earth.
right. Well, the point to it is let's say we were at that 3,000 foot level and all we were looking at was ocean. No mountain in the distance, nothing. We're not going to know that there is an inferior mirage there. We're going to go up there and we're going to get a theodolite out and we're going to calculate the dip to the horizon, not understanding that what we're actually looking at is an inferior mirage.
Can you not think of a way to resolve that problem?
Well, you wouldn't have a way to resolve that problem if...
Oh, I can think of a way to resolve that problem if you wanted. If you were actually concerned about that.
Okay, yeah, go ahead. Tell us.
Stars. Do it at night.
I knew you were going to say that.
Because you can see, because unlike a blurry edge of across Lake Tahoe that's moving and everything, from 3,000 feet, looking out to the ocean, you can see the stars immediately above the horizon, right? You need to, be plenty dark, and you need to probably look away from where the sun is at the moment, so you don't have even the twilight showing. And then you can see the stars, and you can know which stars are which because they've been plotted out, and we know which are which. So you can know whether or not there is a mirage, or if there's something inverted, right? If you've got a layer of inversion, you'll know that because now the stars will be inverted there. If you care.
That's if you see it from that distance. You may not even notice it from that distance.
You may not even notice the stars. You do see the stars.
Well, no, I mean, you might not notice the inferior mirage in the water to the star.
But you would see that the stars are where they're not supposed to be, right? If there was an inferior mirage where the stars have been flipped, for example, you'll see that.
Okay, well, that's something that you can go out and do. Or
that's not me. That's you. That's on you.
You're
the one making these claims. You're the one saying that you can't make observations and predictions based on flat Earth because of these things, right? So here I am one more time. Every time I come back to the server, I ask for a flat Earth prediction, and every damn time I get nothing. No science can be done using flat Earth. That's the conclusion.
Yeah, well, I'm not
science and flat Earth do not combine. Flat Earthers never do science.
Okay.
Never. You want to prove me wrong? Make a prediction using flat Earth. Let's go test it. Prove me wrong.
Can't be done.
Right. Well,
I know.
Can't
be done. Flat Earthers cannot make predictions about flat Earth.
This guy thinks post-diction science. That's hilarious.
That's not post-diction.
Oh, celestial refraction is not post-diction? Okay, cool.
No, it's not. Go do something. Predict something that you've not seen before. I did that. I predicted the dip of the horizon from a location I've never been at. And then I measured the dip of the horizon, and oh my goodness, it matched my prediction because I wasn't there before. I wasn't at that spot before. I predicted the angle of the sun in Antarctica in a location I've never been, and nobody that I have ever seen has said this was the angle to the sun on this day. That's not a post-diction. That's a prediction. I took the model. I used the model to, in the future, make a prediction about something, some observation, some event, and then it matched. So here's this, and that's why it's so incredibly obvious to anybody that understands science that flat Earth cannot do science, because you go make a prediction. Take your model, make a prediction. Never happens. Excuses is all you get. And this is 100% proof that flat Earth has no science. Prove me wrong, make a prediction, and I'll go test it.
Okay, well, I'm not here to make the prediction. I'm just telling
Exactly,
you.
because you can't do science.
Don't
Just doing his
interrupt.
closing thing.
Don't
He's just
interrupt.
doing his
Thank
closing
you.
monologue, bro.
I am doing my
But,
closing thing. You're right.
But so when we can know that there will be a dip in the horizon due to different refractive effects, it should be also up to you to prove that it's not the refractive effects that it's causing the dip in the horizon. Now, I just posted a screenshot from your video.
Sweet reversal of the burden of proof.
Okay.
Love it.
So I
That's
just posted
textbook.
a screenshot from your video. Would you like to look at that, please? In the live text. Everyone else can
Yes.
look at it as well.
Yeah.
So,
Oh, I see it.
can
That's
you tell me
the
whether or not
Calneva Resort,
how
just
obvious
barely above the
we can
horizon.
see that? Yeah, and why? What does an inferior mirage do to the horizon? I mean, what does an inferior mirage do to the objects beyond the horizon?
And what does it do to objects behind the horizon?
Yes.
Well, if there was a dock there, we would see it.
Pardon?
Right? If there was a dock there, we would see it.
So currently, right now,
if the Earth were flat, we would see the
known
dock.
that what McToon is doing is he is admitting that he does not understand inferior mirages.
Let it
And
be
can you-
known that
can
you're
you
putting
tell that
words in
this
my
is
mouth
inferior mirage?
because you can't do science using flat Earth.
Okay, so if I can show you something from 8 miles away where an entire jetty is missing from a 20-foot observer height because of the inferior mirage, when only, according to the globe, 4 feet should be hidden.
So here's
and then
here's the
show you
problem.
on another day, and
We
then
can
listen,
see the waves.
Wait,
You can see the
wait.
waves.
And then on
The
another
waves
day,
prove it's not an inferior mirage because they're
What are you
not just
talking about?
blurred into nothingness. The
Okay.
waves are too crisp. We
Okay,
can
for
see it in the
everyone
picture
who's
there. The
actually
waves are too
looking at
crisp.
what you can see, don't interrupt. So what we can see is we see 2 little white dots above the white line. We see 2 little white dots above the white line. Then go down to the very bottom of that white line, and you will see 2 little white dots underneath it. The 2 white dots underneath it are the 2 white dots on top. We can also see sky below that white line. Why can we see sky below that white line? Because the sky below that white line is the inferior mirage reflection of the sky in between the 2 dots at the top.
How high is that hill? Do you know how high that hill is behind there?
It doesn't
Have
matter.
you been there?
It's
Have you been to
irrelevant.
Tahoe?
It's irrelevant.
Have you been to this dock? Have you looked at the Calneva Resort across that water?
Let's not divert.
Oh no, this is very
Let's go
important.
into the fact that this is
That's not the sky. That's not the sky.
That is the sky.
No, the sky is significantly higher. Lake Tahoe
Well,
is
even if
surrounded
it
by
is.
mountains. It's
Okay,
surrounded by
well, we can't-
mountains.
we
That's
can't
not
see
the
the
sky.
mountains.
That's more behind the resort is what? More dirt. More land.
Okay, well, the blueness that we see, which is washing out the mountains, that blueness that we see, which is washing out the mountains, is also that little square dot of blue underneath.
But the problem
that
is
line.
that the inferior mirage here doesn't do something that it needs to do for flat Earth. Huge amount. There's a huge amount of missing space below the resort there. A huge amount between the bottom of the Calneva resort and the shore. There's not enough inferior miraging there.
Yes, there is. You don't, like I said, you don't understand an inferior mirage. You don't
my
go
goodness.
out, you don't do observations. You don't understand inferior mirages. Okay, I can quite easily show you a scene from 15 centimeter camera height to 14 miles away, where you can see almost to the shore, and then show you from the same camera height where you can't see about 180 feet. I can then also go show you from 20-foot observer height from the same location, where that same distance at now 16 miles away, a bunch of houses that are at 114 feet high are completely gone in the inferior mirage. So yes, an inferior mirage can hide these things in the distance. How high is this hotel thing that you're talking about here?
I think it's 300 feet above the water there. But yeah, Finky, I mean, right here, this wave here, that's that wave that you're seeing is the peak of the curve.
No, it's not. It's an inferior mirage.
That peak is that. No, it's not.
Yeah, we put
all
right. On it right now. No, put 5 grand on. Let's do that.
No, you need to write up. You need to write up the acceptance criteria. Anyway,
right now?
Go right ahead. Write up the acceptance criteria. You won't. I know you won't. Anyway, my email address for you to check it out, sending it to is mctoon@mctoon.net. All right.
Okay. Once again, everyone can actually see more.
I'm gonna head out. I'm gonna head out now. But thanks a lot for proving once again that flat Earth cannot do science. You cannot make any.
Well, that was a good bit of fun.
What happened there? Did he just drop?
Yeah, he's on the stream.
He left? Right. Yeah, clearly. I mean, any moron with 2 eyes can actually look at that image that I just put in there. And you can see the 2 dots on top, and you can see the 2 dots right underneath. That sheer fact that white line has that little gap in the middle is absolute proof that this is an inferior mirage. If someone can't see that, they're either blind or they're retarded.
No, dude, that's Earth curve.
And the point of where this inferior mirage is
I can't see it.
Is not Earth curve.
Dude, that's not Earth curve. If you think that's Earth curvature,
who just said they can't see it?
That was Finky.
Finky, you see where that little, how it's like a rectangle? You can see how it's a rectangle, right? That white line.
I see 2 white lines on the right side. I see a little brown.
So yeah, Terry.
Can you circle it? Let's just circle what you're talking about.
Terry posted it. All right, I'll go in. Give me a minute. You guys can just go on and talk about something else. I'll go on mute and I will.
Yeah, the thing is, you can show literally bottom up obstruction on a lake. Does that mean that there's Earth curve between you and the end of the lake? Or does that mean that there's optical effects that can occur when you have the convergence zone, which is where the sky meets the ground, according to the observer, and you would have effects like, for example, over a lake, you have cool water beneath the air, creating that effect where it looks like there's a marine layer, even if it's only like 100 feet or 200 feet away. You can create bottom-up obstruction. Does that mean there's Earth curve there? No.
Concave Earth has light bending up, and in concave Earth we would get this effect that you guys are describing. So this doesn't prove FE. And the game is not just to disprove the globe.
I think that's the game, because we don't know what the entirety of Earth is yet, but I'm down to figure it out.
I don't want to ruin the fun, but like the only way you're gonna disprove the globe or destroy the globe is by having a better model, not just finding poking holes and nuances.
But that's I mean, I don't need to replace a theory in order to be skeptical of one.
I mean, you kind of do if you want people to accept it, right?
Well, that's retarded.
So like the
like people have jobs to do. Like people, we had this conversation yesterday. Like there's people whose responsibility is to plan flight routes, and if you say there's like flat or the globe doesn't work, they're not going to care what you have to say. They have to still have to do their job.
But that's not the point of me saying that you don't need to replace something in order to point holes in it, because what's wrong with not knowing something? For example, the entirety of Earth, where we live, are people that uncomfortable with the idea of not knowing, that they need to just jump onto any idea that they possibly can in order to feel a sense of comfortability? That's weak.
Well, I mean, like I said, the people that plan flight routes, they have something that works right now.
Yeah, they use the stars. That's all based off the stars. The GPs are literally based off of a conceptual model. The lat long system, that's all based off of the stars. Nothing to do with the shape.
It's just I see where you're coming from. You're not wrong ultimately, but like realistically, it's not going to happen until a better model replaces it.
But why would I replace a lie with a different lie? Because I'd be lying if I would, if I have a model that could replace it, that could replace reality. No, you're never going to actually have a model that can fully represent reality. You know what I mean? And not only is the globe wrong in terms of like its presumptions, but its fundamental, concepts, like the idea of the spherical shape and the radius value, right? Which is the radius value is implemented in so many different things that it would collapse the entire, foundation of assumptions that was built on it. So it'd be like a house of cards, and people are scared of that because
People are scared of it. They're scared of it. This is the reality. They're scared of it. So you're gonna have to have a better model. No, I didn't say you have to explain the whole fucking universe. You have to have a better model in order for the globe to be destroyed. The humanity, no, people are not just gonna see. They're not gonna bend the leg and just fucking say I give up. The only way to move forward is to have a better model than the globe, even a better globe model. I know that's like ruining the fun and this like that I'm just being realistic. It's not going to happen until a better model that's more predictable is presented. Not just poking holes.
If you don't have a map, nobody's going to take it seriously. And if you're just like, it's just about debunking the globe, like nobody's going to care if you can't. Like the first question about
if you state that people's utility as far as their work function is concerned is based on this globe model, it doesn't really mean all that much. People compromise themselves for professional reasons all of the time. They don't notice things. They're not concerned about it. They just, at the end of the day, as long as it supposedly kind of quote unquote works, their remedy, their solution is provided, and they receive their paycheck, and there is no need to sort of reprimand them or correct them at the back end. So this whole idea of basis of like a model on utility is a futile endeavor. Socially speaking, that's got to be the absolute truth.
Most people don't think. I don't think they think through it that far. And there's people like the people that work at
that's
companies
the problem.
That put
They don't think through it that far.
People work at companies
anomalies.
that put satellites up in space, and like you're going to come and say, well, space doesn't exist, and they're going to be like, well, bro, I just put a satellite up there yesterday. Like they're just not going to you're not going to get people to give it the time of day when they are like this other system already works.
But Finky, let me give you an example. I'm sure you've probably heard this before. I'm sure someone has mentioned it before. An example: if I found out that I was adopted,
the purple parents. I've heard it.
Okay,
we've all heard it 100
okay,
times.
so why are you guys ignoring that analogy? I'll explain it for those who haven't heard it. So if I have if I find out my parents were actually not my real parents. Okay, someone told me, they showed me the paperwork. Here, this is how you know these guys aren't your parents. Okay, so who are my real parents then? Oh, I don't know, but this shows that your parents are not your parents. Well, until you find me my real parents, they're going to be my parents for now.
Yeah, it's a good analogy.
Well, imagine that you look exactly like your parents and you have the same like family traits. You have like
Irrelevant.
everybody's like these are obviously your parents. You look exactly like them. And then somebody else comes
Irrelevant.
along
They're
and
not
says,
my
well, here's the
parents.
piece of paper that says that they're not your parents. Like you're not gonna like you. I don't think I would care.
Yeah, but it shows definitive proof that you were adopted. But are you going to close your eyes and put your head in the sand and say, I'm not adopted until you find me my real parents? Then I can replace them.
No, I'd say probably the adoption proof is fake.
The adoption proof is fake.
Yeah, it's probably like CGI. Like if I look exactly like my parents, I would be highly skeptical of somebody that came and said otherwise.
What if they told you?
But there's a major flaw because flat Earth doesn't have absolute proof that the globe is not real. All flat Earth has is it would be like you saying, well, I have a bald spot and my so-called parents don't, so that must mean that I'm not. They're not my parents.
Yeah, I agree with
That's
that.
about what flat Earth has.
I understand the idea and the notion of staying in the realm of I don't know is scary and uncomfortable, and people have been here for years in this discussion. I totally understand where you guys are coming from, but here's the reality, right? The globe was never proven to begin with. So you guys don't understand.
Sure, well, like
Okay, sure.
it was, but all right.
Okay. The
You wanna
world's
touch
not
on-
going to move forward until a better model is put on the table, and that's just how it is.
I don't see what's wrong with what practical uses we have already with the quote unquote model that we're using right now. Because when you talk about navigation, that's using the stars. When you talk about making maps, guess what? Also using the stars. When you talk about timekeeping, hey, guess what? You're also using the stars and well, the heavens and the sun and moon more specifically. But nothing would really change. All that we have that's changed is our philosophical and conceptual perception about where we live.
Distances
Yeah, but
have
even your
changed.
model requires like massive corrections even of the stars to make it work on flat Earth. Like in the southern hemisphere,
What do
you
you?
look
I don't have a
opposite
model,
directions.
dude. My model is real. There is no model. It's reality.
Effie, we're talking about something beyond you. We're talking about flat Earth. We're talking about flat geometry.
It's flat. Isn't in the globe conception that it's locally flat everywhere?
No,
Okay.
we're not. I'm not playing these semantic games, man. I'm not
No.
playing these
This is
games.
important because
There's
how
no
can
flat
you
Earth.
make
There's
any?
no flat Earth map where people don't look opposite directions to see the same star. Like that's broken. And and what you guys do is you just run from it and say, well, I don't have any model. Like people aren't gonna.
All maps are
Nobody's gonna
based off of
adopt
the
that. They're not gonna
stars,
care.
dude.
And everybody
Literally
has
every single
to.
map.
Flat Earth has to every time you come up with one thing, you have to change everything else. You say, we say, well, we see 24-hour sun in Antarctica. The sun basically follows the same degree across the sky as it moves. It don't speed up or slow down as it gets further away like it should if it's moving flat overhead over top of you. It don't grow in size and shrink in size. It may very, very little, but not like it's coming from a distance, going over your head and moving away from a distance. Every time we say stuff, though, it's always, you have to change one thing to make something else fit. That's not how reality works. Everything would fit together if it was real.
Listen, every single measurement that we take in terms of like trying to find the curvature, where's the actual curvature? Where is it? I truly mean that. I truly mean that question when I say that.
It's in all kinds of places.
Show me where. What method?
Geodetic surveying.
Geodetic surveying is one of them.
Okay,
And
geodetic surveying. How is that different from plane surveying?
you
It's a lot
treat Earth-
stricter.
y-
Like
yeah,
the
you-
requirements is like about 1,000 times, 2 orders of magnitude more strict.
Yeah, and you don't make any assumptions about anything. You work in full 3D coordinates rather than making false assumptions about there being a particular thing about the vertical axis.
I know it's frustrating. Sorry, Jesse. Sorry, go ahead. Sorry.
I was going to say, another thing is, I mean, we all agree that a star has, at a given point in time, has a GP, right? A point on the ground where you can stand, and you will be, directly under it. Your friend can stand there with you. He also will be directly under it. If you take 3 such GPs and stars, and 3 such observers, one under each star at the GP, and each person measures the angle, the right to left angle to those 2 stars, because we agree that those 2 stars are both over their GP. That is where the star is above the ground. Those 3 people can measure the angles between each of the other 2 stars, and if it's over any significant area, it will add up to more than 180 degrees. And obviously, you know that a triangle on a plane has to add up to 180 degrees, not more than 180 degrees.
No, I totally understand that concept of geodetic surveying. It would have to equal more than 180 degrees, right? But you also have dips as well, where it's less than. It's not exactly flat either. I totally understand that. Here's the problem, though. When you're talking about geodetic surveying, what is it used for? And when is it used?
I just dropped a diagram, a chart, in response to the thing you said. The only times when spherical excess is less than 180 is when the margin of error, when the triangle is too small and the margin of uncertainty is larger than the spherical excess would be. As you can see, once the area of the triangle is large enough to overcome the margin of uncertainty, then it is always, always, always in the excess.
Okay, I understand that. What I'm asking is, when is geodesic surveying actually used?
Geodetic?
Geodetic surveying.
Right. Whenever you need to survey areas larger than plane surveying will be accurate for, or if you need extreme accuracy.
So anytime there's areas larger than when you would use plane surveying, when is that? When? Well, give me an example.
Across the United States, or like surveying across Australia or continents.
You never do that. No surveyor has ever done that ever.
Like
Across the state. No.
No, they did that in 1800s in the U.S. and in 1927.
They didn't do it in a single shot. It was a project, but they did survey.
Yeah, but plane surveying is the same.
Yeah,
Take
it's
a bunch
between
of different
stations. Correct. You have stations, right? That basically, for example, you create. Like they used to use lights back in the day, like they used to call them lamplighters or whatever. But you basically flash your light. Okay, I'm this far away. I'm at this mountain peak. Okay, now you're creating a triangle, and then you're zigzagging across a certain portion of land. That that creates basically a datum. Right now, that datum is just a datum. But how can you actually make that useful? Well, when you take that datum and you reference it, you basically plot it out according to like whatever, a WGS 84, or at the time like the North American datum 27, and then whatever plot of land you're actually adding to that, you have to see where it's different. What elevation am I referencing to as I'm taking these new measurements, right? So you're basically taking one reference point, starting from the coast, right, to another, to another, to another, to another. That is all plane surveying.
I mean, it's all straight lines, but
Exactly.
One question I've had is, so so they add in spherical excess, right? Take that out.
Add it in.
Yeah, so go coast to coast, but then take all the spherical excess out. Do you think you'll end up back up at sea level?
Yeah. The spherical excess has nothing to do with reality. It comes from trying to compare and contrast it to the chosen ellipsoid or geoid that you're trying to basically use as a reference.
Yeah, I agree. They assume it, and then they add it in. So I'm saying take it out, but when they add it in, then they ended back up at sea level. You get that, right? Like if you took that out, you'd go coast to coast, and then on the other coast, you'd be like, 1,000 feet elevation, looking at the ocean.
Could you check out my screen share, Biasticles? And you touched on two different topics relating to surveying, and I'd like if I may to briefly address them both. So let me know when you got. Okay, cool. So let's say a surveyor, they start with a point, and they measure the distances of three sides of a triangle. Now they've got a triangle. Okay, that without them knowing the exact angles of the sides or a small area, that doesn't necessarily tell them what if it's a flat or globe. But what happens is then they do another triangle.
Yep, exactly.
And another triangle.
Yep.
And they just keep doing triangles.
That's like the triangulation, yes.
Now, when they close this last one, they're going to know if it's flat or a globe, assuming it's over a big enough area. Because if this is a globe, for example, this middle point will be higher. Like if the circle lies along a plane and it's on a globe, then the center point will be higher, the sagitta, right?
Hold on, you said the sagitta would be higher if it was a globe in the center.
Right. In other words, let's say we're looking at
But Jesse, you do understand that is a fallacy, right? It's parts of the whole fallacy, or
no? Here, let's look at a side view. if we look at a side view of all these lines, here's, the one in the middle here, and then, then all the other ones around the outside, but it's all going to be on a plane. But if Earth is a curve, then here's these, and these lines are going to be a longer path than they would be if they're a straight line. See what I'm saying? So this is looking at the side view, then here's the perimeter.
Yes. No, I understand what you're saying, Jesse. The spherical excess comes from plotting those triangles on a referenced ellipsoid or geoid. I already said that. But that's my point, though. They went in like pre-assuming that they live in a ball.
The thing is, if you don't do that, your network doesn't close.
That's what I'm saying.
It closes.
Like you get fired you'd get immediately fired as a surveyor because your network wouldn't close.
No, it's not, dude. There's so many datums across the world where that locally, and when I mean locally, I'm saying in their local area, before they transpose it to, compare and contrast it with the WGS 84 or, some other type of datum, because what you're doing is you're basically transferring the real raw data, which the real raw data is all triangles. Period. That's
I agree.
it. Like, yeah, that raw data then has spherical excess when you plot it on some type of ellipsoid or geoid. But the geoid and ellipsoid are pre-assumed. You're making that's a fallacy, dude. That's a part of the whole fallacy. That's like measuring a part of my pool, right? And saying, okay, if I measure 10 feet on one side of my pool, and then I measure 2 feet on the other side, right? But there's still 20 feet left. I'm not going to make a claim to the entirety of it. That would be a fallacy. That's a part of the whole fallacy. Just like if I measure the area of New Mexico, right? Let's say I measured all of New Mexico, all of it, right? And I measured it to be completely plane, right? Completely planar and flat. I would be making a fallacy if I said that, well, that means that Earth is flat in its entirety.
If you measured New Mexico, if you went on to geodetic surveying and you did it to the requirements of the spec, like a first order triangulation, and you found it to be flat, I would become a flat earther. Even New Mexico.
That's all they're at. That's exactly what it is. Ask Jesse. All the first order is a triangulation that uses plane surveying.
It is, but if you don't account for spherical excess, your network doesn't close.
Why are you accounting for spherical excess?
Because the Earth is round.
That's an assumption.
I know, but if you don't do that, your network. Hold on, but you keep glossing over this. If you don't do that, your network won't close.
What do you mean your network won't close? It's already
the
closed.
Triangles. You'll get to the end of you'll get to the end of your network. Your triangles, and your last one will have too much error, and your boss will say that
where's the error coming from?
I'm trying to show you that.
I know where the error comes from. I'm just asking Finky. The error comes from when you reference it to an ellipsoid or geoid of your choosing. There's no error in the raw data. It's raw data.
The triangles have to close. And if
those are closed, look at his screen.
Well, I know those are made up triangles.
That's exactly how it works. The spherical excess comes from when you plot it on a geoid or ellipsoid. How many times do I have to keep saying it?
No, you should. What you should do is you should get a set of flat triangles, and you should try to do this on like a basketball, and you'll see that they don't fit.
I don't assume the basketball, bro.
No, I'm saying if you assume that it's flat and then you try to put it on a basketball, it won't fit.
No,
and vice versa. Yeah, so that's my point. If you go out and you try to do geodetic surveying and you assume the Earth is flat and you don't account for spherical excess, then it doesn't work. Like the angles.
Why would I assume
work.
Spherical excess if I don't assume that we're on a ball? What if I just take the triangulation, right? The raw data.
You should do it.
Because that's exactly what it is. That's first order measurement. I'm just measuring the surface, bro.
You guys should do it. You should do it and see what you get.
There's a real world implication. It's one thing to do the math and hide in the math, but it's going to show up in the real world.
What are you talking about? Hate breaker?
He's agreeing with me. He's just saying if you go out and you assume it's flat and it's not, then it's not going to work. It doesn't work. You can't map a flat surface onto a round one or vice versa.
Yeah, they're not just like equal to each other. You can't hide it. There's no hiding it. It's large scale, there's no hiding it. It's not going to
Depends
work.
on where you are in the world, dude. There's dips
Zoom
and
out,
valleys.
zoom out your scope of stop doing short scale. Do half the world, full world.
What are you talking, dude? All measurements are local. Every single one. Every single one, dude. You tell me when you figure out how to measure half the world at once.
Well, if the approximately 1 degree per 60 nautical miles is true.
Conceptual model.
But, I mean, is it true? Can I go out, pick a star, put a tape measure on the ground, start walking, reeling out 600 miles of tape, or 600 nautical miles of tape, walking directly towards that star, and then remeasure the angle to the star? Will it be really close to 10 degrees different? Will it? I mean, if that's physically true, then we can actually measure distances between any 2 points on Earth by both looking at the same star at the same time.
What does that have to do with the shape, though?
That they're not.
That allows us to measure the distance between 2 points.
Yeah, but that's not mutually exclusive. You can use the stars to calculate a distance. The celestial sphere is just that, right? You break it down. That's why it's 60 nautical miles per degree, right? That's why it works out, because 360 degrees, right? Times that by, let's see, 360 degrees. What am I thinking of here? Yeah, 15 degrees per hour. Let's see here. So if you have 15 degrees per hour, that's 24 hours. Yeah, that adds up to 24 times 15. That's 360, right? The sun moves about, quote unquote, 1,000 miles per hour, right? This is what you guys say. It's rotating 1,000 miles per hour, spinning 1,000 miles per hour, or 15 degrees per hour. Why is it 1,000 miles per hour? Because it has to be, right? Because if it's 1 hour for every, meridian, essentially, then it would have to equal 1,000 miles per hour because of the circumference that you guys, presuppose. You basically say that Earth is circumference is 24,000 miles and some change, right? That's equivalent to the 15.4 degrees per hour rotation. Okay, all of that is a ratio. All of that is a ratio. You can insert whatever the heck you want in there. Doesn't matter because it's a ratio.
The
It's all
ground,
conceptual model.
the real distance matters. The ground, the distance matches the sky.
The real distance, I will agree, is measured by taking GPs of stars in terms of long distances, in terms of references. But here's the problem, though, right? Here's the problem. Once you assume after a certain point, for example, if I have a 2-degree star on my horizon, like Pikes Peak, for example, then I am assuming that 12 hours from then, it's going to be 88 degrees at a certain point or location, completely opposite of it. Right? But we would never know that that would be true because it would be daytime. So the zenith positions of these stars that we're basically assuming to be true, it's all a concept. It's all calculations. All I need is one star in the sky to reference to calculate the rest.
So, you agree then that we can tell our distance quite reasonably from the GP of a star by simply measuring the zenith angle and multiplying by 60 nautical miles per degree?
Yeah, you can make it's give or take, yeah.
Okay, so let's say we have we do this 4 times, and I've drawn a square. I hope it's square. Let's say we measure the sides of a triangle that's 1,000 miles along each side. Using an angle to a star, we wait until there's a star GP at each corner, and we stand at the other corner, and we then measure, and we know that it's 1,000 miles. Okay. On a flat plane, let's say we also measure diagonally. We measure the zenith angle to the star that is kitty corner from us, and we do that both ways, right? Now we know that the sides are each 1,000 miles. Do you know what the kitty corner distances will be on a flat plane?
You're saying it's 4,000 miles between each point?
No, it's each side is 1,000 miles. It's 1,000 miles wide and 1,000 miles high.
Oh,
and then the question is, what is the kitty corner distance on a plane?
On each side, it's 1,000, right?
What's that?
Each 1,000?
No, it's longer. The kitty corner is always longer than the side of a square.
I don't know what you mean by kitty corner. The diagonal?
Oh, diagonal, yes. You never heard catty corner? Anyway, yes, the diagonal. I do apologize. How long is the diagonal on a 1,000-mile square?
Oh, God.
It's
Just tell me.
1,000. Yeah, it's 1,000 times the square root of 2. It's like 1.414, whatever. It's basically 1,414 miles, kitty corner or diagonal.
1440. So it's like a square root of 2. Okay.
Yeah, it's the side of a square times the square root of 2 is equal to the diagonal.
Okay.
Of a square.
I got you.
So, but that's only on a
That's
flat
always
plane.
the case when it comes to 4 sides.
For equal
square.
sides.
For equal
Yeah,
sides, right?
Yes.
Okay.
4 equal sides on
I'm
any
with you so
square
far.
on a plane. Okay. Now, if we do that on a globe or on a sphere, and I'm drawing a side view now, you can see that the sides are going to be taking one path, but the kitty corners will be going up and over and down. So there's going to be the kitty corners will actually be longer on a sphere than they would
You
be.
equivocate this to like arc length and chord length or whatever kind of thing.
Right. In other words, then the arc length is longer than the chord length because there's a non-zero sagitta, right?
But see, that's okay. So this is the issue, though, and this is where I have the issue. You're assuming that.
Assuming that you mean in geometry?
Yeah, because
Oh,
in reality, if I were to measure 1,000 miles, which is, I mean, that you can't. That's not. First of all, that's not going to happen. Like that far away. Like if we were to empirically actually measure it, right? That's just not going to be that distance. The spherical slice, in a sense that you're portraying here, right? I get what you mean. Of course, it would be longer, right? The diagonals would be longer because it has a bulge. It's going over a spherical path, essentially an arc path, an arc length. I get that, but that arc length is all based off of the stars. But go ahead. Go with your example. I'm already jumping ahead. Go ahead.
Okay. Well, so 1,000 miles would only be about 14.5 degrees from straight up. So if we're standing on this corner and we're looking at the star whose GP is 1,000 miles away, we're almost looking straight up. We're looking less than 15 degrees from straight up. So there's going to be virtually no refraction affecting its apparent location. It's going to be a very high quality angle as far as celestial navigation goes. So we definitely can measure this distance using the angle to that star. If the GP is here and we're here, we can very accurately measure the angle to that star, the zenith angle to that star, and very accurately determine that this is 1,000 miles. And we can do the same thing from kitty corner to kitty corner. That would only be, let's see, what's 14, 20.5 degrees. So from kitty corner or from diagonal end to diagonal end would be 20.5 degrees down from straight up. So we absolutely can measure the distances of these 6 line segments. And it is physically geometrically different if it's on a plane as compared to, say, a sphere. And so if you were to actually in the real world go out and do this, you would find that these two diagonals were longer than the 1414 and longer by the amount that the globe model predicts. So geometrically would match a ball that size.
No shit. That's a celestial
didn't
sphere.
we already say the feasibility of actually doing this measurement in reality is unattainable?
It's completely obtainable. People have been using sextants for hundreds of years, or at least 100 years. I don't know how long, but a long time, and measuring such distances with extreme accuracy. And the star
You're basically saying the surface of Earth better matches the celestial sphere if we treat the Earth as a sphere. Yeah, no shit. But is that the truth?
Well, I mean,
better matches the celestial sphere if we treat the Earth as a sphere. Yeah, no shit. But is that the truth?
And a star
you're
that's
basically saying the surface of Earth better matches the celestial sphere if we treat the Earth as a sphere. Yeah, no shit. But is that the truth? Better matches.
And measuring such distances with extreme accuracy. And a star
you're
that's
basically saying the surface of Earth better matches the celestial sphere if we treat the Earth as a sphere. Yeah, no shit. But is that the truth?
Well, I mean, if you're still agreeing that we can use the angle to a star to know the distance between the observer and the GP over 1,000-mile distance.
I mean, 1,000-mile difference, right? That's big, right? Divide that by 60. How many degrees of declination are you talking about from star to star?
Straight overhead would be 0 degrees of zenith.
Right.
Straight
That's your
overhead.
zenith. Mhm.
Okay, so this one would be 0 if it's right over you.
1,000.
This
That
one would be
like
15. This one would be 15 degrees down from straight over. So just like, I mean, it'd be 15 degrees away from straight over you. That's like almost straight up. That's no problem. That's not that far.
Okay, so now you got 15 degrees between point to point, corner to corner. Okay. Now in that 15 degree angle difference, I should say, the instrument that you're using in order to get that angle, what kind of error margin is it? Now let's just say it's a degree. That's 60 miles of error margin.
What? Oh no, sextants are way better than a degree.
I think they're an arc minute, I'm pretty sure. 5, most of the let me see.
And then if you use a theodolite, then you get to the nearest few arc seconds. I can tell you this. I measured the zenith angles to a few stars from my backyard one night and gave them to Bacon, and he solved it for my location within like 500 feet or something. So, yeah, you might have an error of 500 feet, but over 1,000 miles, that's a very small error.
True. Okay, so now, all right, over 1,000 miles. I'm just trying to think of the feasibility. So are we assuming we're over water?
It doesn't matter, because you're looking up at a star that's almost overhead. It's 15 degrees from overhead, or 20 degrees from overhead if you're doing kitty corner or diagonal.
See, the thing is, Jesse, if I'm using a zenith, right, a star that's at my zenith, and then I'm using another star that's basically at 75 degrees, right? Because that's what you're saying, right? It's basically saying from 0 to 15 degrees away, 1,000 miles or whatever. That's what I don't understand, because we can't use stars like that in that range because there's not enough change that we can actually see with the sextant that we use. Like, we have to use stars that are in a certain band in order to see the actual degree change, because when it's overhead like that, it doesn't actually equivocate to 15 degrees per hour. 15,
That doesn't make
15.4
it.
degrees per hour.
I mean, but so you're saying that that if it's that close to overhead, that it is that you can no longer know your distance from the GP by the zenith angle? I mean,
you would
we
have
agree
to
that
use that as like a reference point.
Well, let me ask this: if you're at the GP, would it be directly overhead? And conversely, if it's directly overhead, would you be at the GP?
Yes. Yeah.
Okay. So if you went
It's directly
600
overhead. Right.
So if you went 600 nautical miles away, that would be, or I'm sorry, if you went
That'd be 10 degrees. Yeah.
Okay. So I'm not sure what the problem is. So then if 10 degrees is 600 nautical miles, then couldn't 14.5 degrees be 1,000 US miles? I mean, if that's the way it works, that should be the way it works.
No, I get that. I completely get that. I'm just trying to see, because there's instances where that 15.4 degree relationship doesn't actually hold true in all instances.
Can you name one?
Yeah, the celestial theodolite.
Okay, and is that straight up, or is that way down low where everybody knows that there's strong refraction?
Well, even if there is refraction, it still is. It's not following that 15.4 degree relationship. The refraction corrections are inserted in order to keep the model in its usefulness. That's the only reason why celestial refraction is even a thing that can be assumed and just put in. It's all based off empirical observations. It has nothing to do with the actual refractive effects of the atmosphere. All it has to do with is keeping that relationship intact.
Okay, so the reason I picked a star being straight overhead, or very close to it, was to eliminate
the
amount of...
Have you looked up...
How much correction would you apply for a star that was directly straight overhead?
It's extremely minimal. No, I get
what
you're saying.
It'd be 0. If it's straight overhead, it would be 0, because which way are you going to correct it? It's straight overhead. You're not going to correct it any which way. So if you look up the amount of refraction correction for 15 or 20 degrees from straight up, it's going to be extremely, extremely low.
I got you. Listen, I have to
That's
run.
what's that?
But I have to run. But the thing is, Jesse, whether you assume, whether you assume that relationship or not, that's that relationship that you have with angles to the stars, and you assume that that's intact or not. At the end of the day, you cannot make a claim about the entirety of something by just measuring a bit of it.
Could I make a real quick closing before you run?
I gotta go. But yes.
Okay, so if you see my screen share, I picked 4 stars and put observers at the, simulated observers at the GPs of them, and used Stellarium to read the altitude angles to them across the United States. And I used 60 degrees per 1 degree per 60 nautical miles, and with that calculated distances. And next slide. So then I took and I cut strips of paper, the exact scale lengths, based on those distance measurements of those 6 lines, the 4 sides and the 2 diagonals, and I cut them out, and you can see they lay on the globe, but they do not lay flat. So that's my point. This is one way that anybody could actually objectively know without depending on anybody else if it is a physically flat or physically spherical surface. Anyway, thank you.
Thank you, Jesse. All right. Later, guys.
Seriously, he's dodged it. There's been at least 6 occasions of it, so that's why I brought that up first before I brought anything else up. But if
I had no idea you were all steamed up with him already.
Oh yeah, you can see. Sorry, but he was already acting. He called me an asshole, but he was already acting like an asshole to everyone else. But either way, if you go into the live stream text, you'll see my message. Probably only about maybe 12 or 13 messages up. You'll see a screenshot that I put. It's got arrows and stuff on it.
Uh-huh.
Can you see the red line there?
Uh-huh.
Okay, so the red line there is the fold line. You can see the arrows that are on diagonals are pointing to little white dots above the fold line and little white dots below the fold line. You can see the little white bits? There's 4 of them.
Yeah, almost. I mean, I can see where you could see that if you wanted to.
Yeah, if we had the raw footage, obviously we would be able to see it better. But then you see the 2 vertical lines, how it's pointing to that little white, almost a square in between, like the blue almost square in between those 2 white dots at the top. And then when you go to the bottom, that arrow that's pointing to that little kind of blue square right there as well. They're the same point. That's a mirror image. That is a mirage. This is a inferior mirage. So what he's actually gone out and done is he's gone out on a day where the water temperature was quite a substantial amount warmer than the air temperature. This is actually a really obtuse or very large inferior mirage. You can see by how much water or how much the mirage goes below that red line, below the fold line. If it was a smaller inferior mirage, then the distance between that red line and the water would be smaller. And as the horizon moves further away, that distance between the fold line and the water would get smaller and smaller and smaller until there was no difference between that, because there would be no mirage. So this here is an inferior mirage. And this is why he doesn't want to go on about it. And this is why he just totally dodged it and didn't even want to talk about it, and then just left straight after I start talking about this, because he didn't want to go into this. Now, I understand that the 2 little dots at the bottom are quite faint, and this is not the most, it's a little bit of a blurry image because it's coming from his screen. It's from our video looking at his screen, so it's obviously not the best image. We would need to see the actual raw image or the raw footage, but I guarantee you 100%, I would bet my house on this, that that's an inferior mirage.